Hello there, and welcome to Science for Sleep, where curiosity gets cozy and science takes the scenic route to slumber. You're in just the right place to settle in, slow down, and let your thoughts drift like a feather on still water. Tonight, we're taking a very different journey. Not up toward the stars or across the vastness of space, but far beneath us, where light doesn't go and sound barely follows. The subject of tonight's slow and silent descent is something very real, very far away, and very easy to forget exists. And yet it's as much a part of our world as anything on land. This place has no sky. It has no wind. It has no sunrises, no trees, and no seasons. But it is alive. It's called Challenger Deep, the lowest known point on Earth's surface, located within the Mariana Trench in the western Pacific Ocean. A trench so deep that if you placed Mount Everest into it, its peak would still be submerged under thousands of feet of water. But we're not dropping in all at once. Let's ease our way down into the idea, into the darkness, into the silence. Before we go further, I'd love to know, where are you listening from tonight? And what's it like there, in your corner of the world? Is it dark out yet? Or are you letting this play in the quiet hours of morning, before the day has really begun? Either way, I'm glad you're here, and I hope this slow voyage downward offers you a kind of comfort. If you find this kind of calm relaxing, or if you're just quietly fascinated by what might be living in Earth's most unreachable places, I'd be ever so grateful if you gave the video a like or subscribed. It helps this sleepy little science corner find others like you, curious minds who might need a peaceful pause. Now make yourself comfortable, breathe slowly, and let the room fall away. Because the story we're exploring tonight takes place in a space that almost no one has seen. It begins not in laboratories or classrooms, but beneath more water than most of us can truly imagine. Challenger Deep isn't just far. It's deep in a way that doesn't make sense until you spend time with it. It's not just depth in numbers, it's depth in pressure, depth in isolation, depth in geological time, and depth in mystery. If you've ever stood at the shore and looked out over the ocean, it can feel immense. But what you see, that endless blue stretching to the horizon, is only the surface. Most of Earth is ocean, and most of that ocean is open depth, a kind of vertical desert. What's even more strange is how much of it is completely unexplored. The deep sea is, in many ways, Earth's own version of outer space. Close, constant, but mostly unreachable. Challenger Deep lies within the Mariana Trench, itself a geological scar, a place where two tectonic plates meet, and one dives beneath the other. It's shaped like a long, crescent-shaped groove in the seafloor, over 1,500 miles long. But what sets Challenger Deep apart is that it's the very bottom of that trench, the bottom of the bottom. To reach it, you'd have to travel nearly 36,000 feet straight down. That's about 11 kilometres. The numbers start to blur after a while. Feet, meters, miles. They all begin to feel meaningless once you've passed the point of sunlight, the twilight zone and the midnight zone, which ends far above where we're going. As you descend, the water gets darker, colder and heavier, not just metaphorically but physically. The weight of the water above you presses down with force you don't encounter anywhere else on Earth. At the deepest point, the pressure is more than 1,000 times what you feel at sea level. That's the equivalent of 8 tons per square inch. Imagine a school bus balanced on your thumbnail. That's the sort of pressure we're talking about. And yet, somehow, life exists there. That's what makes it worth visiting, even if only in our minds. The conditions seem absolutely hostile to life. No light, freezing cold and immense pressure. And still, organisms not only survive, but thrive. Some of them are so alien to us that we wouldn't even know where to begin describing them. They're not just bizarre looking. They function on principles and adaptations we're only beginning to understand. But before we talk about what lives down there, it helps to understand what kind of place it is, and what it's like to get there. The name Challenger Deep comes from the HMS Challenger expedition, which sailed in the 1870s. The ship was a floating laboratory, and during one of its soundings the crew dropped a weighted line into the ocean to see how deep it went. Somewhere near the Mariana Islands, the line kept going and going. It marked the first measurement of what we would later come to know as the deepest part of the world's oceans. At the time, the tools were crude, the measurements uncertain, but the idea stuck. Decades later, better technology confirmed it. There was indeed a location deeper than anywhere else on the planet's surface. Since then, only a handful of missions, and even fewer people, have actually gone all the way down. It's not just rare, it's rarer than walking on the moon. The very first descent to Challenger Deep happened in 1960 during the Cold War. A Swiss-designed bathyscaphe called the Trieste carried two men, Jacques Piccard and Don Walsh, down into the trench. It took them nearly 5 hours to descend, and they only stayed for about 20 minutes before coming back up. What they saw through the small window was mostly mud, but it was the pressure, the darkness, and the quiet that left the greatest impression. The bottom of the world wasn't lifeless, as some had assumed. They reported seeing something like a flatfish stir in the sediment, a simple movement, but enough to upend theories about the limits of life. Later, scientists debated whether it was really a fish or a misinterpreted image. But that small flicker of life, whether real or imagined, was enough to light decades of scientific interest. Years passed. Technology improved. In 2012, filmmaker and explorer James Cameron made a solo descent to Challenger Deep in a sleek green submersible called the Deep Sea Challenger. He spent several hours at the bottom, gathering samples and footage. What he saw wasn't dramatic in a visual sense. There are no underwater castles or giant monsters waiting in the shadows. Instead, there was silt, darkness, slowness, and yet life. Tiny shrimp-like creatures, worms, microbes in the mud. It's not the kind of environment that dazzles, it humbles. And that's what makes it so strangely compelling. When we picture deep ocean exploration, our imaginations go wild. We think of glowing creatures, ancient monsters, lost cities. And while there's room for wonder, the truth is more subtle, and in its own way more profound. The deep isn't dramatic in the way fiction makes it. It's quiet, it's heavy, it's slow, and yet it's full of life that is utterly alien to what we know on the surface. To get a sense of how alien, think about what most living organisms require. Sunlight is usually high on the list. Photosynthesis, after all, is the engine that powers most ecosystems. But in Challenger Deep there is no sunlight. None. Not even the faintest trace. That part of the ocean is in what scientists call the Hadal zone, named after Hades, the ancient Greek god of the underworld. It begins at 6,000 metres deep and includes the deepest trenches. In this zone, light does not penetrate. The temperature hovers just above freezing, and the pressure is enough to crush almost any living thing evolved for the surface world. But evolution is clever. Life down there has adapted. Creatures in the Hadal zone are built differently. Literally. Their physical structures are fundamentally altered to cope with the pressure. Cell membranes are more fluid. Enzymes are stabilised with unique molecules. Some of these adaptations are so specific that if the organisms were brought to the surface, they would disintegrate. Their biology is not just unusual, it's incompatible with our environment. This is where things get interesting. Because if life can exist in Challenger Deep, in a place with no light, barely any food and impossible pressure, then it raises questions about what life can do elsewhere, not just in our oceans, but in the universe. Scientists have started to look at these deep-sea organisms as analogues for life that might exist on other planets or moons. For example, Jupiter's moon Europa and Saturn's moon Enceladus both appear to have subsurface oceans. If Earth's deepest, darkest trench can harbour life, could those alien oceans do the same? The more we learn about life in Challenger Deep, the more we understand how flexible biology can be, And that flexibility is one of the things that make life so resilient and so beautiful. But of course, there's another layer to all this, a quieter one. While Challenger Deep is full of scientific importance, it also holds a kind of emotional weight. There's something about imagining that place, a part of Earth so unreachable, so alien, and yet right here with us, that stirs a very particular kind of feeling. It's not fear exactly, it's not even awe. It's a kind of reverence, like walking into a cathedral made of darkness and time. It's the knowledge that while we live our fast, busy, light-filled lives up here, there is a place where time moves differently, where the water presses in so tightly that every breath of life is a miracle, where light never arrives, and still something stirs in the mud. This journey into Challenge Deep isn't just about discovering new creatures or understanding pressure. It's about remembering that Earth itself still holds secrets, that not everything has been mapped, photographed or named. There are still places where silence reigns, where exploration isn't flashy or quick, but patient and uncertain. And so, as we continue drifting downward, it's worth taking a moment to appreciate the sheer scale of it all. The trench is not a crack, it's a canyon, a place that could swallow whole mountains, where gravity and geology have shaped a world we will never fully tame. And yet, even here, life has found a way. Soon, we'll start to explore what that life looks like, what it eats, how it glows, or doesn't, how it survives without oxygen in the usual sense, how its cells resist being crushed. We'll look at worms, jellyfish, fish with translucent skin, and creatures so strange that they don't fit into any of our mental categories. But for now, just let your mind settle into the idea of being there, at the edge of the known world, listening to the silence, watching the sediment fall like snow in a gravity we cannot feel. Because in Challenger Deep, there are no tides, there are no storms, only stillness, a kind of peace not found anywhere else on Earth. And maybe, just maybe, that's part of why we're so drawn to it. Because in the deepest place, the noise stops. And when the noise stops, sometimes we can finally begin to hear what we've been missing. If you were to trace a finger slowly across the vastness of the Pacific Ocean on a map, you might pass over it without ever noticing. It doesn't call attention to itself. There's no obvious mark, no bright colour or star to say, here, this is the lowest place on Earth. But there it is, quietly waiting, a narrow slot in the ocean floor off the coast of Guam, hidden beneath nearly 7 miles of sea water. It's not a place that was carved by wind or river, nor is it the product of impact or erosion. It wasn't formed in a day or even in a century. It is the result of slow, grinding forces that have been at work longer than almost anything we can remember. It's called a subduction zone, where one of Earth's massive tectonic plates is slowly sliding beneath another. These plates are vast slabs of crust, floating on the hot, pliable rock of the mantle below. When they meet, the denser of the two gets pushed downward, and as it descends, it creates a trench. Over millions of years, the subduction continues, and the trench deepens. The one we're focused on, the Mariana Trench, is the deepest of them all. And within that trench, at its southern end, lies a single point where the descent reaches its maximum depth. That point is what we call Challenger Deep. It's easy to think of Earth as solid, as a sphere of unchanging land and sea. But underneath all of it, everything is in motion. The continents shift, the oceans deepen and rise, mountains crumble, and sometimes, as in this case, the crust itself folds in on itself, disappearing into the planet beneath. That's what's happening in the Western Pacific. The Pacific Plate is sinking under the smaller Mariana Plate, being pulled downward centimetre by centimetre into the Earth's mantle. In human time, that's almost nothing. But given long enough, that gentle downward tug creates something immense. Not just a dent or a ditch, but a trench thousands of kilometres long and so deep it defies intuitive understanding. To give a sense of scale, You could take the tallest mountain on land, Mount Everest, and place it inside the Mariana Trench. Its peak would still be over a mile below the ocean's surface. Commercial airliners cruise at altitudes lower than the depth of Challenger Deep. It is, by every known measure, the most extreme topographical depression on Earth. But despite its dramatic measurements, there's nothing dramatic about the way it appears. If you could drain the ocean and stand at the edge of the trench, it wouldn't look like a cartoonish pit or a sudden drop-off. It would resemble a long, smooth scar, a quiet valley. And down inside that valley, if you kept walking, or in our case imagining a slow drift downward, you'd eventually reach the bottom of the bottom. This place is not defined by how it looks. It's defined by what it represents. It's a part of the world that resists casual understanding. Unlike mountains or rivers or deserts, which we can see and touch and walk across, the trench is hidden not only by water, but by pressure, darkness and distance. It's not somewhere you can casually visit. Not even with specialised equipment is it easy to reach. Fewer people have been to Challenger Deep than have orbited the Earth. Its remoteness is physical, but also mental. It's the kind of place that invites more questions than answers. There's something deeply strange about thinking of the Earth as having a deepest point. After all, we usually think in terms of height, how tall something is, how high it rises. Depth is more elusive, it's less romanticised, more hidden, more difficult to measure and understand. But it's no less important. In many ways, it's more revealing. Because to understand depth is to understand gravity, geology, time, and how the planet is constantly reshaping itself. Not in big, sudden events, but in slow, silent shifts. And so when we call Challenger Deep a hole in the world, we're not exaggerating. That's what it is. A tear in the crust where one part of Earth is diving under another. A slow-motion fall into the planet's interior. A portal of sorts, into a realm where light can't go and pressure reshapes everything it touches. When scientists began trying to map the ocean floor in detail, they used a technique called sonar. It works by sending sound waves down into the water and measuring how long they take to bounce back. The longer the return time, the deeper the ocean at that point. With enough passes, enough pings and enough data, a picture begins to form. A map. Not one with mountains and rivers like those we know on land, but one with ridges, plateaus and trenches. These sonar maps eventually revealed the full depth of the Mariana Trench, and inside it, Challenger Deep. Even today, the exact depth can vary depending on measurement methods and ocean conditions, but most estimates place it around 10,920 to 10,935 metres deep, or roughly 35,800 to 36,000 feet. That's a figure that exists on the edge of comprehension. It's so far beyond what we experience in daily life that it might as well be fiction. And yet it's real. It's as real as the air you're breathing. It just happens to be far below you. The word trench might conjure images of narrow, steep-sided slots in the earth, but oceanic trenches are wider than they are steep. The Mariana Trench, for example, is about 43 miles wide. It curves gently like a crescent moon, tracing a slow arc along the seafloor. At its centre, Challenger Deep is not a jagged hole or a sudden abyss, but a smooth depression, muddy, quiet, and shaped more like a trough than a pit. Still, the word hole feels appropriate, not just because it's a literal depression, but because it represents something missing. Not in a negative sense, but in a geological one. A hole where the earth is folding into itself. A place where surface becomes interior. A place where the rules change. The pressure at that depth is difficult to describe. It's not the kind of pressure you feel in your ears when swimming in a deep pool. It's not even the kind of force that crushes a can or dents metal. It's beyond what most materials can withstand. At nearly 16,000 pounds per square inch, the water presses in from all sides with a weight that would instantly collapse any structure not specifically engineered to resist it. That's why so few vessels have gone down there. and why the ones that do look more like fortified capsules than submarines. The human body is not built for those pressures. Even robotic systems can struggle. Every piece of equipment, every camera, every sensor has to be specially designed, tested, and protected against crushing failure. And yet, in that environment, life exists. That fact continues to astonish scientists. How can anything survive in a place so cut off from the rest of the biosphere? With no sunlight, very little food, and near freezing temperatures, it seems uninhabitable. And yet the trench is alive. Not teeming with life, perhaps, but sustaining it, quietly, steadily, without spectacle. It helps to think of the ocean in layers. At the top there's the epipelagic zone, the sunlight zone. That's where most marine life lives, where photosynthesis happens, where coral reefs and schools of fish make their home. Below that is the mesopelagic zone, or the twilight zone, dim, colder, and home to strange light-sensitive organisms. Below that is the bathypelagic, or midnight zone, completely dark, colder still, and under enormous pressure. But Challenger Deep lies even further down in the Hadal zone, a region so deep that it's named after the underworld of Greek mythology. In this zone, sunlight doesn't reach, ever. The temperature stays just above freezing. The environment is not just dark, it is utterly, permanently black. And yet, life goes on. Bacteria feed on chemicals in the water, crustaceans crawl slowly across the mud. Some organisms live off detritus that floats down from above, tiny particles of dead matter called marine snow. Others rely on chemosynthesis, a process that uses chemical reactions rather than sunlight to produce energy. What's striking about this is not just that life exists, but that it has adapted so specifically. The creatures that live in Challenger Deep are not just slightly different versions of surface animals. They are entirely separate branches of the tree of life, built to survive in conditions that would be instantly lethal to almost everything else. Some are soft-bodied to avoid being crushed. Others have special proteins to keep their enzymes stable. Some are transparent. Some are nearly invisible. Many move slowly. There's no need to rush in a world where time moves so differently. And in that way, Challenger Deep is not just a hole in the world, it's a window into possibility. A reminder that life finds ways to adapt even in silence, even in pressure, even in what seems like absence. The hole isn't empty, it's simply quiet, waiting. Containing not only organisms but answers to questions we haven't fully asked yet. And while we may never walk there, never touch the floor of Challenger Deep with our own hands, the fact that it exists, right now, beneath the waves, gives the world a strange kind of depth, a sense that there are still places where mystery lives, in the darkness, in the quiet, in the hole in the world. There's a certain comfort in being near water. A calm lake, a wide river, or the edge of the ocean often brings with it a sense of peace. The sound of gentle waves, the feel of mist in the air, the slow, rhythmic pull of the tide. These are things we associate with quiet. But water, especially when gathered in great quantities, holds a kind of weight that's easy to forget. We don't often think about what it means to be beneath it, not just by inches or feet, but by miles. As we imagine continuing our descent toward Challenger Deep, something begins to happen. Not in a sudden, dramatic way, but in small, steady increments. The pressure builds. With every metre we drop, the amount of water stacked above us increases. Slowly at first, then exponentially. It's not like climbing down a hill, it's more like standing under an ever-growing mountain, where the air itself gets squeezed out of reach. The deeper we go, the heavier the ocean becomes. At the surface, pressure is simple. It's the weight of the atmosphere pressing down on us, something we're so used to that we don't notice it. Our bodies are built to match that pressure exactly, like a balloon filled just enough to hold its shape without popping. But as we descend into the ocean, something shifts. For every 10 metres, or about 33 feet, the pressure increases by 1 atmosphere, the equivalent of what we feel at sea level. So at 100 metres we're experiencing 10 times that pressure. By the time we reach 1,000 metres, it's 100 times greater. And by the time we reach Challenger Deep at nearly 11,000 metres, we're talking about over 1,000 atmospheres. That's more than 16,000 pounds per square inch, not spread across your whole body, but on every square inch of it. It's not something we can directly feel or imagine. The numbers don't translate into sensation very well, but there are comparisons that help. The pressure at that depth is equivalent to having a stack of about 50 jumbo jets sitting on top of you, or a fully loaded freight train balanced on a coffee table the size of a dinner plate. It's a kind of pressure that changes the rules of matter itself. Metals behave differently, plastics deform, gases collapse. Even the water molecules themselves are pressed closer together. In everyday life, water is considered incompressible, but at these depths, even water begins to give slightly under the weight. Nothing remains entirely unaffected. For engineers, this presents enormous challenges. Any vehicle, camera or sensor designed to reach Challenger Deep must be carefully built not only to resist the crushing force of the water, but to function properly under it. Housings must be spherical or cylindrical to distribute pressure evenly. Materials must be tested repeatedly. There is no room for structural weakness. A single crack, a misaligned seam, or a minor manufacturing flaw can lead to catastrophic failure. Not gradually, but instantaneously. When the bathyscaphe Trieste made its descent in 1960, one of its outer windows cracked during the descent halfway down. The pressure at that depth was already enormous, but it continued increasing with every foot they dropped. Still, they continued, carefully, slowly. And when they reached the bottom, they became the first people to experience that kind of pressure from the inside of a vessel, with nothing but metal and design between them and the most crushing environment on Earth. What makes this kind of pressure so unique isn't just its intensity, it's how constant it is. There's no relief, no fluctuation. At the surface, waves rise and fall, winds shift, weather changes, but down here, once the pressure builds, it stays, hour after hour, day after day. The water presses inward from every direction, without pause, without fail. And yet, within that environment, life has adapted, not by resisting the pressure, but by yielding to it. Many deep-sea creatures have no internal air pockets, no lungs, no gas-filled bladders, nothing that would collapse under pressure. Instead, they are soft-bodied, with flexible structures that don't resist the weight but absorb it. Some use special proteins and organic compounds to keep their enzymes stable, preventing their cells from deforming or malfunctioning under the strain. There's a substance known as piezolites, small molecules found in many deep-sea organisms that help protect against pressure-induced damage. One such compound, trimethylamine N-oxide or TMAO, helps stabilise proteins under high pressure. Interestingly, this is the same molecule that gives fish their distinct smell. The deeper the fish, the higher the concentration. In theory, if you could catch a fish from Challenger Deep and preserve it perfectly, it would have a far stronger, almost overpowering scent than one from shallower waters. That's the chemical footprint of adaptation. These creatures don't struggle against their environment, they are shaped by it. Their biology, their structure, their behaviour, all of it is a response to the weight above. It's not that they ignore the pressure, it's that they are built from the ground up, or perhaps from the ocean floor up, to exist within it. In contrast, most surface life is deeply dependent on the balance of pressure and air. Even small changes can have profound effects. Think of what happens when we ascend a tall mountain. The air pressure drops, our bodies react. Breathing becomes harder. We can feel lightheaded, dizzy, or nauseous. That's from a pressure change of just a few atmospheres. Now imagine multiplying that by 1,000, and in the opposite direction. That's part of what makes exploring the deep ocean so difficult. We can't simply send people down in wetsuits or even in typical submarines. The difference in pressure is too extreme. Every tool, every cable, every battery, and every circuit must be hardened against collapse. Even simple tasks, like taking a water sample or collecting a bit of sediment, require equipment that can survive the journey. But more than the engineering, the pressure shapes the entire experience of the deep. It defines the environment in a way that light, sound, and even temperature do not. It's the most constant presence in that world. It shapes how organisms are built, how they move, how they reproduce, and perhaps most interestingly, how they die. At this depth, decomposition happens differently. Without the usual mix of bacteria and oxygen, bodies don't break down in the same way. In some cases, large animal carcasses, such as whales that sink into the trench, can take years, even decades, to fully decompose. And while that may seem strange, it provides a rare and valuable source of energy for organisms adapted to slow growth and low input. This scarcity of food, of light, of motion, reinforces just how different this world is. It's not just a darker, deeper version of the ocean we know. It's another world entirely, governed by rules we're still trying to understand. Rules that are shaped, above all, by the immense and unyielding weight of the water above. One of the more subtle effects of pressure is on the chemistry of seawater itself. At high pressure, the solubility of gases changes. Oxygen behaves differently. So do carbon dioxide and methane. Chemical reactions take longer. Some biological processes slow down. Others become more energy intensive. The balance of minerals, the way organisms exchange ions, the behaviour of microbial enzymes, all of it is influenced by the physics of pressure. And yet life continues, slowly, deliberately, efficiently. Some of the microbes found in Challenger Deep are capable of reducing metals, using elements like manganese or iron in ways that surface organisms cannot. These processes are part of what's called the deep biosphere, a vast and still poorly understood network of life beneath the sea floor, thriving without sunlight or oxygen. It's possible that more than half of all microbial life on Earth exists in these deep subsurface environments, shaped entirely by pressure and chemical gradients. We often think of pressure as something negative, a force to be resisted or avoided. But in the deep ocean, pressure is not a danger. It is simply a fact, like gravity, like temperature, like time. For the organisms that live in the trench, pressure is not something to be survived. It is something to be used, to be worked with, to be folded into the structure of life itself. In that way, Challenger Deep teaches us something about adaptability, about how life, when faced with unthinkable extremes, doesn't always push back. Sometimes it bends, sometimes it transforms, and sometimes it becomes something so unfamiliar that we can't even compare it to what we know. There's something calming about that idea, that even in the most inhospitable corners of the earth life continues, not loudly, not quickly, but persistently, softly, quietly. Pressed down by miles of ocean, by forces that would crush a human in seconds, these organisms drift, reproduce, feed, and die, just as they've done for millions of years. They don't need to surface. They don't need to be seen. Their world is closed, self-contained, and tuned to pressures we can barely imagine. As we continue to picture our slow descent through that immense column of water, it's worth remembering what's above us now. Not just the surface of the sea, but the sky, the clouds, the stars. All of it, layer after layer suspended above this trench, above this small, heavy pocket of the world, where the rules shift and the weight is constant. There are no storms here, no current strong enough to stir the silt, no tides that reach this far, only pressure, only darkness, and only the quiet movement of creatures who have never known anything else. And that, perhaps more than anything else, is what defines this part of the planet. It's not that it is unreachable, it's that it is untouched, not by choice, but by design. It was never built for us. and yet it exists right now, with its own rhythms, its own weights, and its own quiet, persistent life. As we continue to sink deeper through the ocean, something subtle but absolute has already happened. Light has vanished. It didn't go all at once the way a switch flips in a dark room. Instead, it thinned out gradually, layer by layer, until it simply stopped reaching us. There is a moment somewhere along the descent where your eyes might still search for light, a shimmer above, a pale suggestion of brightness, but that moment ends long before the trench begins. By the time we approach the Hadal zone, light is no longer something that can reach us at all. It isn't dim, it isn't faint, it simply isn't there. The human eye is remarkably sensitive to light. In dark conditions, even a single photon, the smallest measurable unit of light, can sometimes trigger a response in the retina. We're built to seek it out. But in the depths of the trench, there are no photons to catch. Not from the sun, not from stars, nothing from above makes it this far. The ocean has filtered it out completely. At the surface, light is abundant. It reflects off waves, sparkles on fish scales, and penetrates into the upper layers of the sea, where photosynthesis drives entire ecosystems. That layer is called the epipelagic zone, or the sunlight zone, and it only extends about 200 meters down, a tiny fraction of the ocean's total depth. Below that is the twilight zone, where light begins to fade into grey. Below that is the midnight zone, entirely dark save for bioluminescence, and even that is far above where we are now. In Challenger Deep, we are several miles beneath all of it. Light is no longer part of the environment. It's not reduced or obstructed. It's gone. This kind of darkness isn't just the absence of brightness. It's total. It's a world where vision, at least as we understand it, becomes meaningless. Most surface creatures depend on light to see, hunt, navigate, and recognize one another. But none of that applies here. In a place with no light, eyes are optional. In fact, many creatures that live at extreme depths have either severely reduced vision or none at all. There's no evolutionary benefit to maintaining something that doesn't work. So some fish are blind, some are eyeless, others have patches where eyes might have once been, now replaced with sensors that detect vibration, pressure, or chemical changes in the water. This shift away from vision is part of a larger pattern. In the deep, sensory information takes different forms. Instead of sight, many organisms rely on mechanical senses, the ability to detect changes in water movement. Others use chemoreception, a kind of chemical radar that allows them to detect nearby substances, like the scent of decaying organic matter. In these environments, the difference between a meal and an empty patch of mud might come down to a trace molecule in the water, drifting slowly along a current. Some deep-sea creatures produce their own light, not by capturing sunlight, but through chemical reactions within their bodies. This is bioluminescence, and it's found in various forms throughout the deep ocean. But even that has its limits. The organisms at Challenger Deep are so far removed from the rest of the ocean that light-producing species become less common. In an environment with so little to interact with, there's often no advantage in producing light. It takes energy, and energy, down here, is in short supply. Those that do produce light usually do so for specific reasons. Some use it to attract prey. A tiny flicker in the dark might lure a smaller organism closer. Others use flashes of light to communicate with members of their species, though communication, in this context, is likely not social in the way we think of it. It's more about reproduction, recognition, or territorial boundaries. Some creatures use light to confuse predators, emitting a burst of brightness to disorient their attacker and make a quick escape. But even bioluminescence fades with depth. In Challenger Deep, there are fewer species capable of it, and those that can emit light do so faintly, rarely, and with great purpose. Most of the trench is not lit by glowing jellyfish or flickering fish. It's much quieter than that. Most of the time, it's pitch black. Not metaphorically, not figuratively, but completely. The absence of light shapes not only the biology of the creatures here, but the entire rhythm of their world. On the surface, day and night cycle endlessly. Sunlight regulates sleep, migration, breeding, feeding. Circadian rhythms, the biological clocks that guide so many forms of life, are tuned to the rise and fall of light. But in Challenger Deep, there is no dawn, no dusk. Time does not pass in any visual sense. Organisms here do not rely on day or night. Their lives are governed by other cycles: food availability, chemical gradients, seasonal currents from above, perhaps even the quiet passage of larger organisms overhead, long gone by the time their presence is registered. For those of us used to light, it's almost impossible to imagine living without it. But life here doesn't need our imagination. It has its own logic. It has been adapting to this kind of darkness for millions of years. It doesn't resist the absence of light. It simply continues without it. And that, perhaps, is one of the most revealing things about this environment. It challenges our assumptions about what life requires. We often think of energy in terms of sunlight. We imagine the sun as the source of all life, and for the most part it is. On the surface it drives ecosystems, it warms the planet, it powers plants. But in Challenger Deep the sun plays no role. It's too far. Its energy is spent long before it ever reaches these depths. So instead, organisms here rely on alternate sources of energy. Some feed on marine snow, the slow, continuous drift of organic material falling from above. These particles are small, flakes of dead plankton, bits of fecal matter, the remains of surface organisms that have died and begun to sink. It's a slow, sparse rain, and most of it gets consumed long before reaching the trench. But enough makes it through to support a layer of scavengers, organisms that feed slowly, patiently, with extremely low metabolisms. Others feed on the remains of large carcasses, a whale, a shark, a squid, that happen to sink all the way to the bottom. These events are rare, but when they occur, they create temporary oases of life. Entire micro-ecosystems form around them. Worms, crabs, bacteria, and fish gather to consume what they can. In time, even the bones are colonized by microorganisms that extract nutrients directly from the calcium and lipids locked within. And still others rely on chemosynthesis. Some bacteria, for example, can derive energy from chemicals found in the sediment: hydrogen, sulfur, methane. These bacteria form the base of a deep food chain, one that bypasses sunlight entirely. It's slow, chemical, and incredibly efficient. It represents a form of life that is truly independent from the surface. All of this exists in darkness, and not just any darkness, a darkness so complete, so permanent, that it no longer feels like the absence of something. It becomes the default, the baseline, a feature of the environment, not a lack. For scientists trying to study these organisms, the lack of light presents obvious challenges. Standard cameras don't work without artificial lighting, and artificial lighting can disturb or damage fragile species. Many deep-sea organisms are sensitive to light wavelengths they never naturally encounter, so even our attempts to observe them must be careful, measured, and respectful of how foreign our presence is. This makes each glimpse into the trench feel hard-won. Every image, every frame of footage, every recorded observation represents hours of planning, engineering, and slow, cautious deployment. Some missions send robotic probes equipped with special lights and cameras that minimize disturbance. Others rely on traps and sample containers designed to collect specimens without injuring them. A difficult task, given how fragile many of these creatures are. And when samples are brought to the surface, they often don't survive, not because of injury, but because the conditions above are so different. The change in pressure, the sudden exposure to oxygen, and even the presence of light can be overwhelming. Organs rupture, cells collapse. Some organisms simply disintegrate. Others become unrecognizable, their form held together only by the delicate balance of their native environment. This makes studying them difficult. It also reminds us of how narrow our understanding is. These creatures don't just live in darkness, they are of it, built from it, shaped by millions of years in an environment where light is not part of the equation. The absence of light also changes how we think about direction. On the surface, up and down are intuitive. Up leads to the sky, down leads to the ground. But in the trench, where there is no visible horizon, no light to mark position, those directions lose meaning. Orientation becomes fluid. There's no sun to track, no shadow to follow. Movement is guided by gradients, temperature, salinity, pressure, not by vision. It's a three-dimensional world navigated by sense, not sight. There's something oddly peaceful about that. A world without visual noise, without flicker or glare, just slow movement, chemical trails, pressure changes, sound perhaps in faint and distant forms, a kind of stillness we're not built to experience, but which exists nonetheless. As we continue our quiet descent, it's worth pausing to let that thought settle, that somewhere, right now, on our own planet, there are creatures drifting in a space that has never known sunlight. Not once, not even on its brightest day. Their entire existence unfolds in conditions we'd find uninhabitable. And yet, to them, this is home. It's not a place they endure, it's where they belong. In that sense, Challenger Deep is more than a trench, more than a geological feature. It's a reminder that life, once again, finds a way not by reshaping the environment, but by reshaping itself. And so we keep descending, not toward brightness or clarity, but deeper into the dark, where the rules shift, where the senses change, and where life glows faintly, if at all, against the weight of silence. The word deep gets used a lot. We say it when we're talking about emotions, about thought, about water, or about time. It's one of those words that feels meaningful, but not always measurable. But when it comes to the ocean, and especially the deepest part of it, that word isn't just metaphor. It becomes a physical reality, a set of dimensions so extreme that they begin to lose connection to everyday experience. By now, as we've been slowly sinking through layers of ocean, we've long since left behind anything that resembles the world we know. The surface, with its sunlit waves and familiar blue, is no longer part of this place. Even the twilight zone, that dim, filtered region where a little light still penetrates, is now far above us. We are deeper than whales dive, deeper than the resting place of most shipwrecks, deeper than the absolute maximum depth of recreational or even technical diving. We're in territory so far removed from what's accessible to most people that numbers alone start to feel abstract. But let's pause for a moment and try to make sense of them anyway. Because understanding just how deep Challenger Deep really is means translating unfamiliar figures into something that can be imagined, if only briefly. Measured from the ocean surface, Challenger Deep lies approximately 10,120 to 10,135 metres down. That's a little over 36,000 feet. The number varies slightly depending on the source, due to factors like tides, temperature, and the method used to calculate depth. But however you measure it, the result is the same. It's the deepest known point in Earth's oceans. To put that in perspective, the cruising altitude of most commercial airplanes is around 35,000 feet. If you were to suspend a passenger jet above the trench, and then lower it nose first into the water, it wouldn't quite reach the bottom. There would still be hundreds of feet to go. Another comparison, Mount Everest, the tallest mountain above sea level, stands at about 8,148 metres. If you placed it inside the Mariana Trench, its peak would remain submerged under more than 2 kilometres of water. In other words, Earth's highest natural point doesn't even come close to reaching its lowest. Now imagine standing at sea level. You look up into the sky and try to picture the top of a mountain nearly 9 kilometres tall. That's a big stretch for the human mind. Now flip that image upside down, not toward the clouds, but toward darkness, into a space you can't see and would never survive in. That's the scale we're talking about. Of course, vertical distance isn't something most people interact with often. We think in terms of land, length, area, size, not depth. So let's try something else. The Empire State Building is 443 metres tall, including its antenna. You would have to stack nearly 25 of them on top of each other to reach the depth of Challenger Deep. The Eiffel Tower, at around 300 metres, would need to be repeated more than 36 times. Even the Grand Canyon, which looks impossibly vast when viewed from the rim, is shallow compared to the trench. Its average depth is about 1,600 metres. That's less than 1/6 the distance to the bottom of the Mariana Trench. When you start thinking in those terms, the mind pushes back a little. It doesn't really want to picture something that large, that empty, that hidden. But that's part of what makes this place so powerful. Not because it's dangerous or dramatic, but because it challenges scale. It makes us step out of the comfortable measurements we use for buildings, mountains and cities, and it replaces them with a single vertical path made entirely of water and silence. And it's not just the depth itself that matters, it's the environment that comes with it. Temperature, for example, doesn't keep dropping forever. It stabilises at a certain point just above freezing, usually around 2 to 4 degrees Celsius. That cold persists for miles. It's a constant, unchanging feature of the deep sea, and combined with high pressure and total darkness, it creates an environment that doesn't resemble anything at the surface. Even the water itself is different. It moves more slowly, it's denser. It has different chemical properties, different layers of salinity and oxygen saturation. This is a space where things happen gradually, almost geologically, even though it's made of liquid. Organic matter that falls from the surface can take weeks or months to arrive at the bottom. Once it does, it doesn't decay in the usual way. There's little oxygen, few scavengers, and almost no disturbance. A piece of matter can sit untouched for years. That stillness, combined with depth, creates a sense of timelessness. There are no sunrises or sunsets here, no visible currents, no shifting shadows. Everything about the space is consistent, and in that consistency there's a kind of suspension, of motion, of sound, of the passage of time itself. It's not that time stops, it's that the indicators we usually rely on to sense it are gone. The trench itself, though deep, isn't very wide. The Mariana Trench spans about 2,150 kilometres in length, but is only around 70 kilometres across. Challenger Deep, the very bottom, is even smaller, roughly 11 kilometres long and 1.6 kilometres wide. If you could walk it, it would feel like a small valley rather than a vast plain. But walking is, of course, impossible. There is no ground in the way we usually mean it, only sediment, layers of compressed material built up over millions of years. It's soft, fine, and cold. It doesn't reflect light. It doesn't shift underfoot. It's more like wet dust than solid ground. And floating above that floor is an ocean column thousands of meters high. Not a column in the architectural sense, but in the physical one. A vertical body of water pressing downward, dense with weight, stretching all the way up to the world we know. From the perspective of an organism living at the bottom, the rest of the ocean might as well be another planet. Nothing from the surface reaches it easily. Sound, for example, behaves differently with depth. At certain levels, sound can travel far, even across entire oceans, due to a phenomenon called the SOFAR channel, but Challenger Deep lies below that layer. What sound does reach it is distant, muffled, and almost indistinguishable from background pressure. The creatures that live here aren't shouting across the dark. They move slowly. They don't chase. They don't flee in dramatic bursts. Instead, they drift, feel, sense. Some filter particles from the water. Others lie motionless until food floats past. There's no urgency, just adaptation. This brings up an important idea, that depth isn't just a measurement of distance, it's also a measurement of difference. The deeper we go, the more the rules change. Vision becomes useless. Sound becomes distorted. Pressure reshapes matter. Chemistry alters behaviour. Biology evolves along unfamiliar lines. A fish at the surface and a fish at 10,000 metres may both be called fish, but they are fundamentally different life forms. Their organs, skeletons, metabolisms, and cell structures have adapted to environments that could not be more different. One is shaped by light, motion, and seasonal variation. The other is shaped by darkness, stillness, and the crushing permanence of depth. So when we ask, how deep is deep, we're not just asking about numbers, we're asking about thresholds, points beyond which familiar things become strange, beyond which the known becomes alien. And Challenger Deep represents the furthest of those thresholds. It's the limit of where life, as we currently know it, has been found on Earth. The furthest point below sea level where a living organism has been observed. It marks the outer edge of the biosphere, the zone where life can exist. What lies beneath it, in theory, is rock, the crust, and then the mantle. But those regions are not yet accessible, not with our current technology. So Challenger Deep remains the bottom of the known world, the place where depth stops being potential and becomes boundary. Of course, that boundary may shift. Future missions might probe deeper into the sediment. New equipment might reach further into the rock. But for now, this is the deepest we can go. Physically, technologically, and perhaps conceptually. And that makes it a kind of frontier. Not one filled with flags and monuments, but one that sits quietly at the bottom of a trench, defined by absence of light, of motion, of noise, but not of life. Because even here, at this extreme, life has taken hold. It has grown soft skins, slow metabolisms, and strange shapes. It has let go of the surface rules and written new ones. That's the real measure of depth. Not just in distance, but in change. How far do you have to go before the familiar becomes unrecognisable? How much pressure, darkness, and isolation does it take before biology breaks and rebuilds itself? Challenger Deep answers those questions not with declarations, but with examples. With creatures that have never seen the sun, with sediment that has never been stirred by weather, with water that has been cold and still for longer than we've been writing history. And the deeper we go, the more we realise that deep isn't a fixed number. It's a shifting threshold, defined not just by metres and feet, but by how far you must travel before the world stops looking like the one you know. There comes a point in human exploration where imagination is no longer enough, where curiosity becomes commitment. That point in the story of Challenger Deep happened in 1960. Until then, the trench had been mapped in theory, charted by sonar, hinted at in depth readings. But no one had actually gone. It was a measurement on paper, a number in a report. But numbers, as powerful as they are, can only go so far. To really understand the trench, not just in terms of data, but as a place, someone had to descend into it. And eventually someone did. It was a vehicle unlike any other, designed for a very specific task, to survive the impossible pressure at the bottom of the ocean. It was called Trieste, a deep-diving research bathyscaphe, developed by Swiss physicist Auguste Piccard and later purchased by the United States Navy. It wasn't sleek or fast or glamorous. It looked more like a floating cylinder attached to a large metal float. But it was built for one purpose, to go deeper than any human had gone before. The crew consisted of two people, Jacques Piccard, the son of the vessel's designer, and Don Walsh, a US Navy lieutenant. Their mission was both simple and historic: descend into the Mariana Trench and attempt to reach the bottom of Challenger Deep. On the morning of January 23rd, 1960, they boarded the vessel and prepared to drop. The descent would take hours. There was no quick plunge, no dramatic speed, just a slow, steady sinking, like falling in slow motion through liquid darkness. Inside Trieste, Space was limited. The pressure sphere, the part where the crew sat, was only about 7 feet wide. Walls surrounded them on all sides, thick and round, designed to evenly distribute the immense force pressing inward. Outside the sphere, a larger float was filled with gasoline, chosen not for its flammability, but for its incompressibility. It provided the necessary buoyancy to balance the descent. Communication with the surface was limited. The sound had to travel through kilometres of water, distorted and delayed. There were no live video feeds, no constant updates, just a crackling radio line and long stretches of silence. As they sank deeper, the world grew quieter, colder, darker. At about 9,000 metres, something unexpected happened. A loud crack echoed through the cabin. One of the outer plexiglass windows had fractured. It didn't breach the pressure sphere itself, but the sound and suddenness of the event was a reminder of where they were, in an environment where the smallest failure could mean instant collapse. Still, they continued downward, not recklessly, not with bravado, but with the kind of steady resolve that deep exploration requires. The descent took nearly 5 hours. There were no windows to watch the outside world drift by, no glowing landscapes, just dials, gauges, and the sensation of falling without movement. As they neared the bottom, the descent began to slow. Eventually, after hours of gradual sinking, the vessel touched down. The gauge read 10,116 metres, a depth that placed them, for the first time in human history, at the very bottom of the ocean. The seafloor, when they reached it, was not dramatic. There were no cliffs, no trenches within trenches. It was flat, soft, covered in fine sediment that rose into a cloud when disturbed. The lights on the exterior of the vessel illuminated a small cone of space, maybe a few feet wide, and within that cone something stirred. Later reports described it as a kind of flatfish, a simple movement in the mud, just enough to suggest life. The observation was debated later. Some scientists argued that no fish could survive at that pressure. Others believed it might have been a different kind of organism altogether, or even a trick of light. But the effect of that moment was lasting. It hinted at life not just surviving, but persisting in the most remote part of the world. The crew stayed at the bottom for about 20 minutes. There wasn't much they could do. The sediment clouded their view. The equipment was limited, but the goal had been achieved. They had arrived. They had returned. The ascent took just over 3 hours, faster than the way down, but not fast by any other standard. It was still careful, still deliberate. When they reached the surface, they had made history, and returned to a world that could only guess at what they had seen. In the decades that followed, there were no immediate follow-up missions. Challenger Deep remained untouched. For more than 50 years, no other humans would visit that point. The reasons were technical, financial, and philosophical. The ocean is vast and resources are limited. Deep-sea exploration is expensive and offers few immediate returns, but the interest never disappeared. It waited, quietly, like the trench itself. Then, in 2012, another descent was made, this time by a solo pilot, filmmaker and explorer James Cameron. He piloted a submersible called Deep Sea Challenger, a sleek vertical vessel engineered specifically for the mission. Unlike Trieste, which relied on steel and gasoline, this vehicle used new materials, new designs, and advanced electronics to manage the descent. Cameron's dive was faster, more automated and more thoroughly documented. He brought back samples, video footage, and hours of data. But the experience remained deeply personal. He described the descent as lonely, otherworldly, a sense of moving not just downward, but away. And yet, despite the gap in time between the two dives, more than half a century, the environment at the bottom hadn't changed. The same darkness, the same pressure, the same silence. Nothing in the trench marked the passing of time, it simply waited as it always had. Since then, additional missions have reached Challenger Deep, some piloted, some robotic. In 2019, explorer Victor Vescovo made multiple dives in a submersible called DSV Limiting Factor, part of the Five Deeps expedition. His vessel, built to withstand repeated descents, allowed scientists to collect new biological samples, map the seafloor in greater detail, and demonstrate that sustained exploration at this depth was now possible. Each mission added new data, new images, and new insights. But the experience of descent remained essentially the same: long, slow, quiet. There is no turbulence in the trench, no updrafts or sudden currents. The descent is governed entirely by buoyancy and gravity, with minor adjustments from the vessel's controls. It feels, according to those who have done it, like falling into stillness, a kind of downward drift, measured not in speed, but in distance from everything familiar. Temperature drops gradually, not suddenly. The cold seeps in slowly, surrounding the vessel like a blanket of dense fluid. Lights, when used, pierce only a few feet ahead. Sound is minimal. Outside, the ocean is silent, and the vessel itself hums only faintly. The sound of machinery and monitoring systems keeping steady watch. From inside, the descent can feel isolating. There's no sky to look up at, no visible horizon, just instrumentation and the steady passage of depth readings. Meters tick by, pressure increases, the vessel adjusts, and at a certain point there's a shift in thinking. Above a certain depth, the ocean still feels like part of our world, but below it something changes. The environment becomes so different, so absolute, that it no longer feels like a continuation. It becomes a realm of its own, a different kind of space, not one designed for us, but one that exists regardless of our presence. And yet, we go. Not because it's easy, not because there's something waiting to be claimed, but because descent is part of discovery. It's the act of going where data says you shouldn't, just to see if life, in some form, has made different arrangements, and it has. Every mission into the trench brings back new evidence that life persists, in the sediment, in the water, on the surfaces of rocks, and in the microscopic currents that drift just above the seafloor. It's not dramatic, it's not crowded, but it is there, and each descent brings us closer to understanding it. Because reaching Challenger Deep isn't about conquering a space, it's about observing it, quietly, slowly, with care, not to plant a flag, but to ask a question, not to announce, but to listen. The further you go into the ocean, the less you hear. The world above, with its wind and engines and conversations, fades behind layers of water that absorb and scatter sound. Ships vanish into distance. Waves lose their energy. Even storms become muffled, their noise absorbed long before reaching this far down. Eventually even the sea itself becomes quiet. By the time you've reached the depth of Challenger Deep, almost all familiar sound is gone. Not muted, not faint, gone. This is not the kind of silence we experience in a quiet room or a secluded forest. It's not the background hush of night in a rural town, or the muffled calm of snow falling outside a window. Those silences are filled with small sounds. The creak of a floorboard, the rustle of leaves, the pulse of blood in your ears. But in the trench, the quiet is of a different kind. It's created by the weight of kilometres of seawater pressing down in every direction. That pressure doesn't just affect matter, it affects sound itself. Water is denser than air, and as you descend, that density increases. Sound still travels. In fact, in some conditions, it can travel farther underwater than it can through air, but it bends and refracts. It takes on a different quality, and below a certain point, most of the sources that generate sound no longer exist. There are no surface waves to stir turbulence, no whales to call, no ships to hum and rumble. Even the deep-diving animals that live at intermediate depths don't usually come this far down. So what's left is pressure, darkness, and an acoustic stillness unlike anything on the surface. If you were somehow able to sit at the bottom of the trench, inside a safe and insulated vessel, you wouldn't hear the ocean. You might hear your own equipment, the systems keeping you alive, monitoring your instruments, circulating air. But outside that protective shell, the water would offer no signals. There would be no ambient hum, no distant rumbles, just the near-complete absence of any recognisable sound. Some researchers describe it as eerie, others as peaceful. A few even find it overwhelming, because silence, true silence, isn't something we're built to experience for long. Our brains are designed to process input, vision, hearing, touch. These senses constantly feed us information about our surroundings. In their absence, the brain starts to fill in gaps. In extreme cases, long periods of silence can lead to auditory hallucinations, phantom sounds, imagined music, or voices that seem to appear out of nothing. But in the context of the trench, that silence is not unnatural. It's simply how the environment functions. In fact, what we call quiet is the baseline here. There is no contrast, no interruption. It's not the absence of sound in a place where noise used to be. It's a default state. A normal condition for a place where motion is minimal, biological activity is sparse, and disturbances are rare. There have been efforts to measure the sound environment in Challenger Deep. Some missions deploy hydrophones, underwater microphones capable of capturing low-frequency sounds over long distances. These devices record for hours, days, or even weeks, capturing the acoustic signature of the deep. The results are often surprising. Occasionally sounds are detected. A distant earthquake, for example, might register as a low rumble. A far-off landslide on the ocean floor might send vibrations through the sediment. In rare cases, human-generated noises from the surface, like underwater mining or sonar pulses, might reach the trench, though heavily altered and weakened. But most of the time, the hydrophones record nothing. Not silence in the absolute sense, but the next closest thing. Background noise levels here are among the lowest measured anywhere on Earth. Even the Arctic, with its frozen stillness, can be noisier due to shifting ice and marine mammals. In comparison, the trench offers a kind of calm that is both physical and perceptual. And this silence doesn't just affect sound, it affects how we think about the space itself. Because so much of how we experience a place comes from what we hear. A city feels alive because of its layers of sound. Footsteps, traffic, voices, music. A forest feels wild because of birdsong, insects, wind in the leaves. A beach feels peaceful because of waves, gulls, and the distant rush of water meeting shore. But in the trench there is no soundscape, no signature noise, and that makes the space feel, to many, unreal. Even for those operating remote vehicles or piloted submersibles, the silence is noticeable. The moment they shut down thrusters, adjust instruments, and let the vehicle hover, the environment becomes still. Some describe the sensation as floating inside a sensory void, movement without vibration, space without sound. For living organisms, this silence is normal. Deep-sea life doesn't require sound in the ways we do. Some species may produce low-level vibrations or communicate chemically instead. Others may be sensitive to motion or pressure rather than noise. But in general, this is a quiet world by default. And for us, as visitors, that quiet can be disorienting. It can remind us of how much we depend on noise to ground our experience. There's also another dimension to the silence, the lack of change. In most environments, sound reflects activity. A bird chirps, a car drives by, a tree creaks in the wind. These sounds mark the passage of time. They show that something has shifted, even slightly. But in the trench, there are stretches of time where nothing changes. No movement, no interaction, no collision of elements to create noise. And that contributes to the unique psychological space this environment creates. It's not just that the trench is deep or cold or dark, it's that it's quiet in a way that removes reference points. There's no sonic context, no background rhythm. It creates a sense of isolation not through distance alone, but through the absence of signals. And yet, there's beauty in that quiet. Because in a world so full of noise, literal and figurative, the idea that there's a place untouched by it is oddly comforting. A place where the earth exists in its most undisturbed state. No music, no motors, no machines, just water, rock, sediment, life, slow and quiet. In that silence there is no need to speak, no need to explain. The environment itself is the message. And for scientists and explorers, that message is powerful. Because silence in this context isn't emptiness, it's presence. A presence so steady and undisturbed that it doesn't need to announce itself. It just is. And maybe that's why the trench captures imagination the way it does. Not because it shouts, but because it doesn't. In the modern world, silence is rare. We fill space with audio. Podcasts, music, notifications, conversation. Even when we seek quiet, it's usually relative. But in the trench, silence is complete. It envelops. It defines the space. It becomes the environment. And for those few who have been there, even if only through machines and monitors, that silence stays with them. It's a reminder that some places on Earth still remain beyond our reach, not in distance, but in experience. That there are parts of the planet where human influence has not yet altered the rhythm, where the natural state is still one of stillness. Down here the rules are different, and life, if it's going to exist at all, must follow them. At the surface, most organisms are shaped by sunlight, oxygen and gravity. They grow toward warmth, move with seasons, and rely on energy passed down from the sun. But in Challenger Deep, none of that applies. There is no sun. There is no meaningful gravity in the way we experience it. There is almost no oxygen. And most importantly, there is pressure, more than 1,000 times greater than what we live under every day. A constant, crushing weight that presses in from every direction, leaving no room for error. Despite all this, life does exist here, but it's not life as we usually imagine it. There are no coral reefs, no colourful schools of fish, no plants waving gently in current. The organisms of the trench have evolved under extremes so total that everything about them, from their shape to their chemistry, is a reflection of that pressure. Scientists refer to this part of the ocean as the Hadal Zone. It begins around 6,000 metres and extends to the trench floor. The term comes from the Greek word Hades, the underworld. It's not a place with a lot of biodiversity, at least in terms of sheer variety, but the species that do live here are some of the most uniquely adapted on Earth. One of the most studied is a type of amphipod, small crustaceans that resemble shrimp. Amphipods are found throughout the ocean, but in the trench they take on new characteristics. Some grow much larger than their shallow water counterparts, a phenomenon called abyssal gigantism. Others are translucent, nearly invisible in the absence of light. Their bodies are soft, lacking the rigid shells of surface crustaceans. That softness is essential. It allows them to flex under pressure without fracturing. Their exoskeletons, such as they are, include small amounts of aluminum extracted from the surrounding sediment. This aluminum helps strengthen the outer layer without the use of calcium carbonate, which dissolves at high pressures. It's a kind of chemical armour, one that only works in the deepest places on Earth. There are also holothurians, deep-sea sea cucumbers that drift gently across the muddy floor. These aren't the colourful, thick-bodied creatures found in coral reefs. They are pale, almost featureless, and slow. Some use small tube feet to inch along the seafloor. Others hover just above it, using gelatinous fins to move through the water with minimal effort. Their bodies are adapted for efficiency, low energy, slow metabolism, maximum survival. Some researchers have observed snailfish at incredible depths, including the Mariana snailfish, which holds the current record for the deepest fish ever captured on film. Unlike the fearsome creatures of ocean myth, this fish is delicate, nearly transparent, and shaped like a soft ribbon. It has no swim bladder, no heavy bones, and no features designed for speed. It doesn't need them. Speed isn't a requirement here. Pressure tolerance is. Inside their cells, these animals contain special proteins and enzymes that would fail in any other environment. At the surface, they would fall apart. Literally. Their molecular structures are stabilized by chemicals like TMAO, trimethylamine N-oxide, which increases in concentration the deeper the organism lives. TMAO prevents proteins from losing shape under pressure. It's also the compound responsible for the distinct smell of fish. So, in theory, if you could somehow bring a Hadal organism to the surface intact, it would smell powerfully, almost overwhelmingly, of fish. That smell is more than just a byproduct. It's the scent of survival under conditions no surface species could endure. But most deep-sea organisms don't survive the journey up, not because they're weak, but because they are completely optimized for the pressure and chemistry of their home environment. When brought to the surface, the difference in pressure is enough to rupture their cells. Organs swell or collapse, gases expand, fluids boil. The process isn't violent, it's disintegration by incompatibility. This is why collecting samples from the trench is so difficult. Special equipment must be designed to maintain pressure during ascent, essentially creating a portable version of the trench environment. These devices are complex, expensive, and fragile, and even when samples arrive intact, studying them requires specialized labs that can simulate the crushing weight of the deep sea. That difficulty is part of the reason we still know so little about the trench's inhabitants. Every new sample, every new image, adds to a very slow and careful picture of life at depth. But the pace is deliberate. It has to be. There's no rushing in the trench. And the organisms themselves reflect that. Many of them reproduce slowly. Some may only have a few offspring in their lifetimes. Others may reproduce asexually or release larvae that drift until they find suitable sediment. It's not yet clear how most Hadal organisms reproduce, because observing them in action is almost impossible. There is no lab in the world that perfectly replicates Challenger Deep. So for now, reproduction, lifespan, and behaviour remain mostly theoretical, inferred from structure, tissue samples, and occasional movement caught on camera. What we do know is that energy is scarce. Food doesn't arrive often, so the organisms of the trench are designed for waiting, for feeding opportunistically, for making the most of whatever happens to fall their way. Marine snow, tiny flakes of dead matter drifting down from upper layers, is a primary food source. It contains organic material, small particles of carbon, fragments of dead plankton. It falls constantly, but slowly, and by the time it reaches the trench floor, it's been picked over by every layer of ocean life along the way. What remains is meagre, but to the creatures of the trench, it's enough. Then there are the rare whale falls. When the body of a large marine animal sinks to the bottom, these are deep ocean feasts. An entire ecosystem will assemble around a carcass. Worms, bacteria, scavengers, and fish, each consuming a different part of the remains. These events can sustain a small population for years, and in the trench, where food scarcity defines life, they are some of the few moments where abundance briefly touches the floor. But most of the time, life here is quiet, minimal, efficient. Every movement is calculated. Every adaptation has a purpose. Even colour disappears. Most organisms here are white, translucent, or pale pink. Pigmentation serves no function in the dark. Bright colours require energy to produce. In a place without light, there's no reason to spend that energy. Eyes, too, become unnecessary. Some species have small vestigial eye spots, remnants of ancestors that once lived higher up. Others have no eyes at all, relying instead on tactile and chemical senses to navigate. Their world is not visual, it's sensed through contact, temperature gradients, and chemical trails. And sound, as previously described, plays almost no role. Communication, if it occurs, is likely chemical or mechanical. Perhaps pulses of movement through the water, perhaps subtle changes in pressure. But there is no calling, no chorusing, just motion and response. That's the nature of life in the crush zone. Not just surviving pressure, but being shaped by it in every possible way. Anatomy, behaviour, even chemistry, all of it sculpted by a force so constant and so immense that resistance isn't possible. Only adaptation. And adaptation here doesn't look like strength. It looks like softness, flexibility, stillness. There's something counterintuitive about that. We tend to associate survival with toughness, armour, speed, aggression. But in Challenger Deep, the survivors are delicate. They yield instead of resist. They conserve rather than pursue. They live long, slow lives with as little waste as possible. And they are ancient. Not individually. Most of them likely live for years, not centuries, but as lineages. These species have existed in one form or another for millions of years. Some may have changed very little since early invertebrates colonized the deep. Their environment is so stable that large-scale evolutionary shifts happen slowly. There's no competition for sunlight, no threat of predators from above, no dramatic seasonal change, just pressure, sediment and survival. From a human perspective, this seems alien. We're built for variety, motion and change. We seek out the new. But the trench does not reward novelty. It rewards consistency. Every adaptation must work. Every trait must serve a purpose. And when it does, life continues. It doesn't flash. It doesn't announce itself. It doesn't demand attention. But it is there, beneath miles of water, drifting in sediment, glowing faintly when needed, feeding patiently on the snow of the sea. We may never catalogue all of it. Some species may only exist in isolated pockets of the trench, undisturbed and unseen. Others may be so rare that they are only observed once. But their presence is a reminder that life, true life, not just survival, is possible even in the most unlikely places. And in that there's a quiet kind of wonder. Because it means that even where the pressure is greatest, even where light has never reached, and even where the quiet is absolute, nature still finds a way to build something that lives. By the time we reach the softest part of the trench, where the pressure has become total, and the dark has never once lifted, there's no longer a need for hardness. Shells break here. Bones crack. Gas bladders collapse. So the animals that survive this deep take a different approach. They don't resist the environment. They dissolve into it. Transparency and softness become dominant traits. Not because they're beautiful or strange, although they are both of those things, but because they work. When every molecule of your body is under stress from the weight of kilometres of water pressing in on you, rigid structure becomes a liability. So many of the animals here let go of the solid entirely. They drift, they wobble, they pulse, they bend under pressure instead of trying to withstand it. Some of the most striking creatures of the trench are completely transparent. Not pale, not white, not colourless in the way ice is, but functionally invisible. Their tissues let light pass through them, not because they're trying to hide, but because light has no real role here. With no eyes to see them and no sun to reflect off them, transparency is not camouflage. It's a structural adaptation, a way to reduce metabolic cost, a way to reduce visibility to rare predators, a way to reduce the complexity of the body itself. Jelly-like organisms thrive under these conditions. Deep-sea jellies, ctenophores, and siphonophores are found throughout the ocean, but some of them are only discovered in the very deepest regions. Their bodies are mostly water. No hard parts, no muscles built for speed, just drifting, contracting, pulsing and feeding. One species, first recorded on camera in the Hadal depths, looks almost like a glass sculpture. A dome-shaped body, faintly glowing, with thin filaments trailing beneath it. These tentacles aren't muscular arms or grabbing tools. They're lined with specialised cells designed to sting, trap, and deliver nutrients inward. But even that process is slow. There's nothing fast about life here. Tentacles, in the deep, are more like sensors than weapons. They serve as tactile extensions of the body, reaching into the dark, detecting the slightest vibrations, brushing across particles, and waiting for something edible to touch them. In an environment where food is rare, waiting becomes a viable strategy. So these tentacled organisms don't chase their prey, they create space, they extend their surface area, they let the ocean bring food to them. Not all tentacled life here is a jelly. Cephalopods, the group that includes octopuses and squids, are also represented in deep-sea ecosystems, though their adaptations are equally extreme. Some deep-sea squid have elongated arms with bioluminescent spots. Others have been observed drifting passively, almost like parachutes, with fins extended to slow their descent. Their eyes, when they exist, are either exaggerated in size or completely absent. Some squids are known to have eye asymmetry. One large eye adapted for looking up at faint light, one small eye for looking down into blackness. In the trench, light doesn't exist from above, so the few cephalopods that remain have likely evolved under a different sensory regime. Some may rely more on pressure detection, chemical cues, or passive movement. There are no rapid escapes, no ink defence, there's nowhere to flee to. So instead of fleeing, these animals often disappear into the background of sensation, barely moving, barely interacting, just hanging in space. Translucency is not limited to gelatinous animals. Some species of snailfish and amphipods also exhibit it. With little pigmentation, their organs are visible through the skin. They have no use for colour in total darkness. They don't need to communicate visually. They don't need to attract mates with display or threaten rivals with patterns. Their lives unfold invisibly, and their bodies reflect that. This transparency has unexpected advantages. It reduces metabolic load. Pigment costs energy to produce and maintain. In a nutrient-poor environment, even small energy savings matter. It also allows for an even distribution of internal pressure. Light passes through, but so does pressure, temperature, and chemical diffusion. In a world without solid boundaries, a boundaryless body can thrive. Many of these creatures are gelatinous in the literal sense. Their bodies are made up of high percentages of water, held together by protein networks that give them form but not resistance. They can expand and contract without damage. They can be compressed without collapse. Their structure is an agreement with the pressure, not a contest. Some species are so delicate that they have never been recovered intact. Even the act of collecting them with gentle tools can destroy their shape. They drift as perfect forms in their native environment, but cannot be preserved in air. Their bodies rely on the fluid around them to maintain coherence. Remove them from it, and the illusion of form disappears. Observing these creatures requires patience. Cameras must be adjusted carefully. Lights must be dim or filtered. The slightest disturbance, a propeller current, a shifted sampling arm, can blow them out of view. Even slight movements in the water column can scatter them or damage them. But when they're seen clearly, they appear as something almost unreal. Not because they're alien, but because they defy the usual categories of life we expect. No skeletons, no shells, no solid mass. Instead, they exist as systems, networks of tissue, feedback loops of response and adaptation. Every part of their body is involved in sensing, feeding, balancing, surviving. There's no division of labour in the way complex land animals have. No limbs that specialise, no organs that centralise function. These organisms are decentralised, distributed. A tentacle is also a sensor. A bell is also a digestive space. A membrane is also a pressure regulator. It's easy to assume these creatures are simple, but simplicity is not the right word. They are minimal, not in the sense of being less evolved, but in the sense of having exactly what they need. No more, no less. That kind of balance is rare in surface ecosystems, where change is constant and speed is often rewarded. In the trench, stillness wins. So these animals float. They absorb. They let gravity and current define their location. Some use vertical migration to their advantage. rising slowly at night to catch drifting particles, then sinking again by day. Others remain near the seafloor, grazing on sediment, filtering microbial mats, or waiting near decomposing material. Their movements are quiet, not just because they're slow, but because there's no need to move more than necessary. Every contraction uses energy. Every adjustment must be worth the cost. Tentacles serve not just as tools, but as memory. The ocean is a space without fixed landmarks. Organisms must use their own bodies to measure distance, location, and context. Tentacles allow them to feel their environment over time, to map the world in strands, not snapshots, to know what's nearby by having touched it, rather than having seen it. Even reproduction follows this softer logic. Some jellyfish release gametes into the water, relying on slow drift to carry them to a match. Others reproduce asexually, dividing or budding off clones that float nearby. Some cephalopods lay small clutches of eggs and then guard them in crevices, using tentacles to protect the developing young. But most reproduction here is private, isolated and unknown. Observing it directly is nearly impossible. The depths are too great, the activity too infrequent. So much of it remains a mystery. What's clear, though, is that these organisms are not fragile in the way we often imagine. They are not vulnerable because they are soft. They are robust in ways that matter here. They can survive conditions that would shatter steel. They can tolerate chemistry that corrodes metal. They can outlive systems that rely on complexity by being simple, distributed, and self-maintaining. And in that way, the transparent and the tentacle dominate parts of the trench. They are not rare exceptions. They are central examples of how life solves the problems of the deep, not by overpowering them, but by yielding to them with purpose. This approach feels unfamiliar to us. Our technology tends toward rigidity, mass, and force. But trench life suggests another model, one that bends, absorbs, and adapts through fluidity. It's a reminder that in environments where everything collapses under pressure, softness can be a survival advantage. So the tentacles drift, the bodies pulse, and life continues, not in hidden corners, but in full acceptance of the space it inhabits. These creatures are not avoiding pressure, they're built to live within it. And as we watch from the safety of armoured machines, it becomes clear that this is not a barren world. It's just one that requires a different kind of vision. Not one that sees edges and outlines, but one that sees continuity. A world where boundaries blur, where form and function merge, where the living and the water become in some ways inseparable. Most fish, when you picture them, have certain things in common. There's a mouth, a pair of eyes, a body that narrows into a tail. Even when they vary in colour, size or shape, most fish still carry that basic set of features. It's part of how we recognise them. But in the deepest parts of the ocean, that familiarity begins to fade. The features become blurred, faces disappear, and in some cases, what remains doesn't even register to the human eye as a fish at all. This isn't an accident. It's not a result of injury or deformity. It's what pressure, darkness, and time do to anatomy when survival becomes the only priority. In Challenger Deep, and in other Hadal zones scattered throughout the ocean, fish do exist. But they do so in forms that are deeply adapted to an environment that doesn't require, and doesn't reward, the typical fish design. One of the clearest examples of this is the so-called faceless fish, first documented by researchers deploying deep-sea equipment in the Western Pacific. The organism was about 40 centimetres long, pale in colour, with a bulbous, featureless head that seemed to lack a mouth, or eyes entirely. In photos, it looked more like a smooth sponge than a vertebrate animal. But it was a fish, specifically a type of cusk eel, part of a family known for living in deep marine environments. And it did have a mouth. It was just positioned on the underside of the body, nearly invisible unless you turned the animal over. The eyes were there too, but deeply recessed and not externally visible. They served almost no function. At that depth, sight is irrelevant. To us, the absence of a face is unsettling. We look for faces everywhere, in people, in animals, even in objects. It's one of the most basic recognition patterns in the brain. When we don't find one, we don't quite know what we're looking at. But to the fish of the trench, faces are optional, unnecessary, possibly even detrimental. Vision requires energy. Eye development uses resources. In a pitch-black environment, those resources are better spent elsewhere. So, evolution trims the excess. Over generations, fish that invest less in facial features, eyes, colouring, expressions, tend to do better. They spend less energy maintaining unused systems. They reduce their metabolic load. They become more specialised, more streamlined in the way that only deep-sea life can be. Some of these species develop extra skin over what used to be eyes. Others lose the nerves and optical tissues altogether. The result is the same, a head that has no visible sensory input. Just smooth tissue, shaped by internal structures and external pressure. And yet, these animals are not blind in the way we think of blindness. They have replaced vision with other senses. Mechanoreceptors along the body detect subtle changes in water flow. Chemical sensors pick up on traces of organic material. Vibrations travel differently at this depth, and these fish are tuned to detect them. What we interpret as a faceless animal is in fact a highly sensitive system, one adapted to a world without light. The structure of their heads often reflects their feeding strategy. Mouths can be located lower, facing downward into sediment, or they may be forward-facing but soft and collapsible, designed to suck in loose particles or small prey drifting nearby. Some mouths are expandable, hinged in ways that allow a rapid vacuum-like action to occur. This is useful in an environment where food is rare and must be captured without delay. Their teeth, if they have them, are usually small or absent. These are not hunters in the traditional sense. They don't bite or chase. Instead, they filter, graze or scoop. Their prey is often microscopic or soft-bodied, and the act of feeding is less a pursuit and more a matter of intercepting material as it floats or rests in the water. Facial musculature also shifts. Expressions, as we understand them, have no place here. There is no social signalling, no need for aggression displays or mating dances that rely on visible cues. As a result, muscles used to move eyes, lips, or other features tend to fade over evolutionary time. The face, in the human sense, simply stops being a focal point. The lack of pigmentation contributes to the faceless effect. Most deep-sea fish are white, beige, or translucent. When combined with an absence of features, this gives them a ghostly appearance. Photos taken under artificial light show these fish as blank, pale masses, with little to differentiate one end from the other. But in their natural state, without light or contrast, they're almost completely invisible. Some species have taken this to an extreme. The Mariana snailfish, found at depths exceeding 8,000 metres, is a master of minimalism. Its head blends smoothly into the body. Its jaw is weak. Its bones are soft. Its organs are suspended in jelly-like tissues that distribute pressure evenly. It's not built for speed, strength, or resistance. It's built to persist. To the untrained eye, it barely looks like a fish. It has no scales. Its fins are small and close to the body. Its skin is translucent, and its face, if you can call it that, shows no visible eyes, no expression, and no defined structure. Just a slight bump where a mouth opens downward, and faint markings where the head begins to taper. These fish live alone or in small clusters, spread out across the sediment. They don't form schools. They don't navigate by sight. Instead, they drift, feed, and hover. They remain motionless for long stretches, expending as little energy as possible. And when disturbed, they move with slow, careful flicks, not to escape, but to relocate slightly and resume their stillness. Other deep-sea species take different approaches to the faceless problem. Some fish retain eye sockets, but the eyes themselves have atrophied into small dots. Others have wide mouths but lack any surrounding features, no cheeks, no jawline, no visible head at all. Just an opening, followed by a tube-shaped body. Functionally, these animals are little more than a digestive tract with propulsion. And yet they thrive. Because in the trench, appearance means nothing. There is no light. No one is watching. No predator is scanning for silhouettes. The only thing that matters is efficiency. How well you can convert rare nutrients into motion. How well you can detect food before it passes. How little energy you can use while waiting. And if that means losing a face, then the face goes. This kind of evolution can be difficult to process. We tend to associate complexity with advancement. We expect animals to become more detailed over time. But the trench teaches a different lesson, one of reduction. Strip away what you don't need, specialise in what remains, and focus every available resource on staying alive. It's not a glamorous path, but it works. The faceless fish aren't anomalies. They're indicators of success in one of the most hostile environments on Earth. Their biology is not a mistake. It's an answer to a very specific question. How do you live when almost every normal rule of life no longer applies? And their answer is simple. You stop playing by those rules. You don't rely on light. You don't waste energy on vision. You don't hunt. You wait. You absorb. You sense. You move only when necessary. And you allow the environment to shape you completely. It's not a life we could survive, but it's life. Real life. Evolved. Specialised. And persistent. And the next time a remote submersible sends back a blurred, drifting image of what looks like a smooth, white lump with no visible features, scientists will pay attention, not because it's frightening, not because it's strange, but because it might be another version of an old answer, a species that found a way to exist at a depth where most forms fail. Faceless fish remind us that vision is not the only path to knowledge, that shape is not always meaning, and that in the deepest places on Earth survival looks very little like anything we're used to seeing. Even in the most complete darkness, light has not entirely disappeared. Not sunlight. That vanished many kilometres ago, filtered out by the upper layers of water before ever touching the trench. But a different kind of light remains, not from the sky, but from the bodies of the organisms themselves. Faint, flickering, often blue, sometimes green, almost always cold, bioluminescence. It's not rare in the ocean. In fact, it's more common than not. At mid-depths, an estimated 3/4 of known species produce some form of light. It serves many purposes: communication, camouflage, predation. But in Challenger Deep, where even biological activity is sparse, it takes on a different character. It becomes less about interaction, and more about subtle signalling, less about display and more about utility. The glow isn't visible to human eyes without equipment. It isn't bright. It doesn't flash across wide distances. But it appears again and again in the form of dim pulses, small dots, or halos surrounding drifting bodies. These signals are not random. They are the result of chemical reactions that have been shaped over millions of years, each serving a specific role in an environment where energy is too precious to waste. Bioluminescence works through a basic chemical reaction. A molecule called luciferin reacts with oxygen in the presence of an enzyme called luciferase. The result is light, real light, not just reflected brightness, but light generated from within. No heat is produced, no flame. This is cold illumination, perfectly suited for organisms that live in a heatless world. Some species produce the light themselves, using internal chemical processes. Others host symbiotic bacteria that generate light for them. In both cases, the result is the same, a small controlled release of visible energy, emitted through specialized cells or organs. But the question becomes, why? Why maintain a system of light in a place where nothing can see it? The answer is layered. First, not everything in the trench is completely blind. Some animals still have eyes, though often reduced in size or function. Others can detect changes in light even without forming images, and more importantly, bioluminescence can serve as a tool for interacting with the environment itself, not just other organisms. One of the most common uses is luring. Some fish carry small bioluminescent organs on extended filaments near their mouths. These lights sway gently in the water, resembling the drifting motion of marine snow or small plankton. Other creatures, hungry and tuned to motion more than shape, approach the light and are consumed. This technique isn't fast. It doesn't rely on chasing or trapping. It's a waiting game. A light held out in the dark, glowing just enough to draw attention without warning. And in the trench, where food is rare and energy is costly, this kind of low-input, high-reward strategy can mean the difference between survival and starvation. Other uses of bioluminescence are defensive. Some species, when threatened, release a cloud of glowing mucus or fluid into the water. It serves the same purpose as an octopus's ink, a distraction. In total darkness, a sudden burst of light is enough to startle or confuse a predator, giving the prey time to slip away. Some use light for counter-illumination. This is a form of camouflage in reverse. In shallower deep-sea regions where faint sunlight still filters down, animals may produce light on their bellies to match the dim glow from above. This makes them harder to see from below. In Challenger Deep, where sunlight doesn't reach, this adaptation is less common, but some species still exhibit faint belly lighting. It may serve as a relic of ancestry, or it might still help in hiding from upward-looking predators that carry their own light detection systems. Communication is another possibility. Short flashes of light could serve as signals, markers of presence, readiness to mate, or warnings to stay away. But proving this is difficult. Most of these behaviours are inferred. Very few have been observed directly, because cameras and submersibles can rarely get close without disrupting the organism's natural behaviour. Still, the patterns are consistent enough to suggest function. Light is too costly to produce if it serves no purpose. In the trench, where movement is slow and interaction is rare, even a single pulse of light can carry meaning. It might travel only a few meters before fading. It might be seen by no one. But when it is seen, or sensed, it becomes a bridge between isolated life forms, a signal in the dark that something else is nearby. The wavelengths used are also worth noting. Most bioluminescent organisms emit blue or blue-green light, which travels the farthest in seawater. Red light is almost never produced because it doesn't penetrate far, and many deep-sea animals can't detect it. This spectral limitation means that deep-sea bioluminescence is evolutionarily tuned, shaped by physics as much as by biology. There are exceptions. Some species, especially those with specialized signaling purposes, produce green or even violet light. These are rare, but when they appear, they often accompany unique structural adaptations, like filters, reflectors, or lenses that shape and direct the glow. One example is the flashlight fish, though it doesn't inhabit the trench itself. It carries a pair of glowing organs beneath its eyes, which it can blink open and shut like eyelids. The principle is the same as in Hadal species: controlled, intentional light. In Challenger Deep, organisms aren't producing light for show. There are no visual predators to impress, no displays, no rituals that require visibility. The glow serves as a tool, part of the animal's basic toolkit for staying alive, a way to find food, a way to avoid becoming food, a way to navigate a world with no landmarks. Some of the most captivating images returned from deep-sea submersibles show bioluminescent organisms passing in front of the camera in complete silence. A drifting jellyfish, pulsing gently, each contraction leaving a brief ring of light behind. A slow-moving worm, glowing faintly along its sides, casting just enough illumination to outline its own body. These displays don't fill the frame. They don't reveal themselves all at once. They flicker, they blink, they vanish. and they don't always return. Some species glow only once, a one-time signal released during stress or reproduction. Others emit light continuously, but only in microbursts too faint for the human eye. The variations are as complex as any other system in biology, but much harder to study. Light that only appears at 10,000 meters below sea level doesn't survive collection. It must be witnessed in place, and that requires technology, patience, and a certain respect for how rare those glimpses really are. We tend to think of light as information. On the surface, it's how we see the world. It provides shape, colour, movement, expression. But in the trench, light is not about seeing. It's about sensing. It's not meant for viewers. It's meant for responses. This changes the way we interpret it. A flash is not a visual display. It's an interaction, an output, a cue for something else to happen. The trench is not a performance space. It's a system, and light is one part of that system. Even the scattered glow of bacterial colonies can carry meaning. Some trench-dwelling crustaceans appear to host small patches of light-producing bacteria in their joints or along their carapace. These patches pulse faintly, and their exact purpose is still unknown. They might serve as bait, or they might signal chemical readiness, a kind of biological status update that only other organisms with similar sensors can interpret. There's a kind of elegance to this system, not in the sense of beauty, but in efficiency. Nothing glows without reason. Nothing maintains the machinery of light unless it gains something in return. The enzymes that make bioluminescence possible must be coded in the genome, produced in the cell, maintained throughout the life of the organism. That's not free, it costs energy. And in the trench, where every calorie counts, those costs are carefully balanced, so the glow persists, dim, intermittent, precisely targeted. It shows us that even in the deepest dark, some organisms choose to make themselves visible, just enough, and only to those who are looking in the right way. That alone says something about life in the trench. Not that it's hiding, but that it's evolved ways of communicating that work in complete isolation. Not with words, not with colour, but with the smallest units of energy turned into signal. To witness it, even through a camera feed, even for a second, is to be reminded that life does not vanish in darkness. It adapts. It invents new ways to interact. It writes messages not in ink or sound, but in flashes of cold light that bloom once and then disappear. And even if we miss them, they were there. In most ecosystems on Earth, food comes from the sun. Plants grow by capturing sunlight. Herbivores eat those plants. Carnivores eat the herbivores. Fungi, bacteria, and scavengers recycle what's left. Even in oceans, most life is still fueled by photosynthesis. Plankton absorbing light, producing organic material, passing that energy upward through layers of marine life. But in Challenger Deep, that entire structure collapses. Sunlight never reaches this far down, not even a faint glow. The trench is pitch black, and it always has been. There is no plant life, no plankton blooms, no algae coating rocks. There's no green, no photosynthesis, no harvest of solar energy. So the question becomes simple and absolute. Where does the food come from? The answer, most of the time, is that it falls. In the absence of light, the only reliable input is gravity. Organic matter from above. Small, dead, broken, digested, drifts slowly through the water column. Scientists call this marine snow. It's made up of particles of decaying plankton, fecal pellets, mucus, and bits of tissue from animals that died closer to the surface. As these fragments descend, they're broken down and consumed by organisms at every level. By the time they reach the trench, they've already passed through many filters. What's left is sparse, but not useless. It contains carbon, proteins, trace elements, enough to support organisms that have adapted to survive on almost nothing. The snow doesn't fall like a blizzard. It's more like a steady, weak rain. A thin, constant drift of particles. Some fall quickly, Some remain suspended for days or weeks. The descent rate varies depending on the shape and density of the particle. Fecal pellets from fish can sink fast. Mucus strands drift more slowly. But all of it eventually moves downward, and some of it reaches the trench floor. There, it settles on the sediment, mixing with the fine clay and a sand to form a thin layer of organic-rich mud. This is where most feeding in the hadol zone occurs, not in the water, but in the top millimetres of the seafloor. Organisms that live here are mostly detritivores, feeding on the accumulated waste of the ocean above. Some, like certain amphipods, burrow through the sediment, extracting microbial life and digestible carbon. Others graze along the surface, scraping together whatever fragments they can. The process is slow. Often, the amount of organic matter available is so low that even a large animal must spend most of its time feeding just to maintain weight. There are also bacteria and archaea living in the mud, metabolizing what little organic matter is present. These microbes are key players in the hadal food web. Some form biofilms that coat rocks or animal bodies. Others live inside the guts of trench-dwelling animals, helping break down material that would otherwise be unusable. These symbiotic relationships are not optional. For many hadal species, internal microbes are essential, partners in digestion that make survival possible. They help unlock nutrients, regulate chemical balances, and sometimes even produce needed compounds that the host can't synthesize on its own. In rare cases, energy enters the trench through larger events. A whale dies. Its body, no longer buoyant, sinks past the twilight and midnight zones, eventually landing on the trench floor. This is called a whale fall, and it changes everything. A whale fall is an ecosystem unto itself. For months or even years, it provides food to a wide range of organisms, from scavenging fish to bone-eating worms. The body is broken down in stages. First, flesh is consumed by amphipods and other mobile feeders. Then, soft tissues inside bones and cavities are accessed by specialized bacteria and worms. Eventually, the skeleton becomes a scaffold for microbial mats that feed chemoautotrophic species. This sudden abundance of nutrients changes local dynamics. Species that are usually rare or dormant may become more active. Some may even migrate short distances to reach the site. But these events are rare. In the entire observable record of hadal exploration, only a few such falls have been documented. Most animals living here will never encounter one. Instead, they depend on consistency, not in quantity, but in approach. Their feeding strategies reflect a world where food is never guaranteed, where survival depends not on what you catch, but on how little you need. Some deep-sea holothurians, sea cucumbers, process sediment continuously. Their bodies filter through mud, absorbing organic particles and excreting the rest. It's not glamorous, it's not efficient, but it works. They move slowly, covering ground over time, digesting a tiny percentage of what passes through their systems. Other creatures form traps, sticky tentacles, mucus nets, or cilia-lined grooves that collect falling particles from the water. These are passive systems. Once established, they require little energy. The organism simply waits for the ocean to deliver food. Even more passive are suspension feeders, animals that hold their bodies open to the current, capturing whatever drifts by. In the trench, where currents are minimal, these feeders must be incredibly sensitive. They rely on turbulence caused by slight geological features or thermal gradients to bring food close enough to capture. Some crustaceans, like certain types of deep amphipods, appear to consume a mix of carrion, detritus, and microbial material. Their stomach contents often contain fragments of protein, bone dust, and even small plastic particles, a reminder that even the trench is not untouched by surface waste. Filter feeding, deposit feeding, scavenging, symbiosis. These are the tools of hadal nutrition. There are no grazers in the traditional sense, no predators as we picture them. Almost nothing here actively hunts in the open water column. It's simply too costly. Pursuit requires speed. Speed requires calories, and those are in short supply. Instead, trench animals are slow. They have low metabolic rates. Some may only need to eat once every few weeks. Others maintain a steady intake of the low-quality food. Their bodies are adapted to make use of whatever's available, no matter how broken down or sparse. This also affects reproduction. In food-scarce environments, timing is critical. Some species reproduce in synchrony with seasonal pulses of marine snow. Periods when surface productivity is high and more organic matter makes it to the bottom. Others hold on to fertilized eggs until conditions improve, using internal stores to support early development. There is no single strategy. But the theme is always the same: conserve, wait, be ready for whatever arrives. One of the more fascinating possibilities in recent research is that some trench organisms may supplement their diets with chemoautotrophy. This is the process of gaining energy from chemical reactions, usually involving hydrogen sulfide, methane or ammonia. While more common near hydrothermal vents, some bacteria capable of chemoautotrophy have been found in hadal environments. If symbiotic relationships exist between those bacteria and trench animals, it could provide a local energy source not dependent on surface input. Evidence for this is still limited but growing. Genetic studies of microbial communities recovered from hadal sediments show enzymes associated with chemical energy processing. If confirmed, it would mean that even in the most food-deprived part of the ocean, there are organisms building organic matter from scratch, assembling life from inorganic ingredients in total darkness. It wouldn't change the scarcity, but it would add resilience, a kind of internal food production that softens the reliance on what falls from above. Still, for most of the trench, the basic equation remains unchanged. You eat what reaches you. You conserve what you digest. You waste nothing. This approach creates strange anatomies: enlarged stomachs, extremely slow digestion, bodies with high fat content for energy storage. Some fish captured from depth retain food in their stomachs for weeks, not because they're lazy, but because the body is designed to extract every possible calorie before moving on. And there is no such thing as selective feeding. Trench organisms cannot afford to be picky. They consume plastic, metal fragments, microfibers, any small particle resembling organic matter. Some of these materials pass through, others remain in the body. There's no filtering system capable of rejecting them, because such selectivity would require more energy than it saves. The result is a population living on the edge of sufficiency, a constant negotiation between input and output, between what the ocean provides and what the body requires. It's not a life of abundance, but it is a life of precision. Feeding here is not a behaviour, it's a state of being. Organisms exist in a constant relationship with the environment, shaped by the flow of nutrients, the drift of particles, and the occasional arrival of something more. They do not compete in the way surface animals do. There is little benefit in conflict. The energy cost is too high. Instead, they coexist. Each species finds its layer, its method, its particle type. The trench is not a battlefield, it's a shared resource, sparse but navigable. And in that space, life persists, not by conquering, not by growing faster or feeding more, but by taking less, moving slower, needing only what can be found. In most ecosystems, movement means life. It signals foraging, fleeing, mating, exploring. On land and in shallower waters, animals move constantly. They chase food, patrol territory, shift with light, respond to threat. There's motion in every direction, every moment. But in Challenger Deep, where energy is rare, light is absent, and every calorie is earned at a cost, stillness has become a way of life. It isn't just that some creatures rest, or that they're slow. It's that many of them barely move at all, not because they can't, but because not moving has become their most effective strategy. Every beat of a fin, every shift of a tentacle, every muscle contraction has a price. In an environment where food may arrive once in a week or a month, or not at all, movement is a luxury. And over time, life has evolved to treat it that way. Many hadal animals exhibit what biologists describe as low baseline activity. Their heart rates are minimal. Their respiration, if it exists in a traditional form, is slow and often undetectable. Their internal processes are suppressed, not because they're dying, but because that is the condition for continuing to live. They have adapted to an energy economy where waste is not just dangerous, it's unsustainable. For animals near the trench floor, especially those that remain close to or inside the sediment, staying still isn't just economical, it's structurally built into their bodies. Some species of sea cucumbers lie motionless for hours or days, filtering only the upper millimetre of sediment as it passes beneath them. Others extend feeding tentacles in a radial circle and hold them completely still, letting the ocean bring food to them. If there is no current, they wait. If nothing drifts past, they continue waiting. There is no urgency. Snailfish, some of the few vertebrates adapted to these depths, spend most of their time near the bottom, resting. They do not swim far. Their bodies lack gas bladders, and their muscles are weak. Buoyancy is managed by body chemistry rather than internal air. Their motion is limited to brief adjustments, a small rise, a slow descent, a flick of a fin to rotate or shift laterally. These are not hunting motions. They are about positioning, maintaining access to nutrients, adjusting to a slight change in slope or current. From above, through the lens of a deep-sea submersible, these animals appear as still as stones. Sometimes they don't register as alive at all until a slight disturbance, a tool arm, a light, a burst of current, causes them to shift slightly. Even then, the movement is minimal, a slow rise, a turn, a slow retreat to a new patch of mud. Then the stillness returns. This stillness is not inactivity. It's not a passive absence of motion. It's a refined strategy, a choice made over evolutionary time, reinforced by every environmental constraint. Stillness, in this context, is an adaptation, just as much as pressure resistance or chemical digestion. It's something the body learns to do well. Some creatures take it further. Certain hadal polychaete worms bury themselves completely in sediment, forming small tubes or tunnels with a narrow opening to the water above. They extend a feeding appendage or sensory filament and then remain still, sometimes for days, awaiting the arrival of food particles. The rest of the body stays hidden, motionless, protected by mud and distance. Crustaceans do the same. A burrowed amphipod may sit with only its antennae extended, unmoving except for the faintest twitch now and then to sense chemical changes. In the deep sea, there is no visual tracking of prey. There is no sprint to close a gap. Detection must happen through touch, vibration, or chemical diffusion. All of these are aided by stillness. Movement introduces noise. It disturbs the surrounding water. It creates turbulence. To detect others, an organism must first reduce its own interference. This applies not just to predators, but to everything. Even filter feeders benefit from not moving. Passive filtering, catching particles as they drift through, depends on minimal disturbance. The more an organism flaps or pulses, the less effective its feeding structures become. And at hadal depths, where currents are slow and unpredictable, the best strategy is to wait, extend, hold. Let the water move past you. Do not chase what you can catch by doing nothing. The biological mechanisms that allow this kind of stillness are diverse. Metabolism is key. Many deep-sea species have extremely low metabolic rates. Their bodies run in slow motion. Oxygen uptake, if relevant, is minimal. Heat production is negligible. Some animals rely almost entirely on anaerobic metabolism, energy systems that function without requiring high oxygen levels. Muscle structure also changes. Fast-twitch muscle fibers, which produce rapid movement, are rare. Instead, hadal animals often have a higher proportion of slow-twitch fibers. These are more efficient for sustained, low-intensity activity, holding a posture, keeping a fin extended, making slow adjustments. Their nervous systems are tuned not for reflex but for economy. Buoyancy control plays a role too. On land, staying still means fighting gravity. In water, it means managing flotation. At the surface, fish use swim bladders, air-filled organs that help them stay suspended at chosen depth. But in the trench, swim bladders don't work. The pressure is too intense. Gas would compress to nothing. So trench fish use chemical buoyancy instead. Their bodies are filled with low-density lipids and water-rich tissues that match the pressure of their environment. This allows them to remain suspended or rest on the seafloor without effort. They don't need to flap to stay afloat. They don't sink uncontrollably. They are essentially in balance with the water around them. That balance makes stillness possible. External factors support it as well. The trench is quiet. Seismic activity may cause occasional disturbance, but in general, the water is calm. There are no tides or strong waves at this depth. No sudden temperature shifts, no storms. Everything is slow, and the animals reflect that slowness. This does not mean they are incapable of movement. Many hadal species can move when needed. They can respond to threat. They can reposition for feeding. But the movement is always measured, controlled, minimal. When a submersible's lights illuminate a scene, it sometimes captures moments of response. A fish shifting just out of frame, a jelly drifting sideways, an invertebrate contracting slightly into its burrow, but rarely does anything flee. The typical response to disturbance is withdrawal, not escape. Part of this is about risk. Movement exposes the animal, it disrupts camouflage, it announces presence, it burns energy, and in most cases it doesn't improve survival odds. So natural selection favours animals that do less, that sit longer, that learn to exist within stillness rather than outside of it. Even reproduction reflects this. Some species release gametes passively, letting them drift and mix in the water column. Others brood eggs internally, maintaining them with minimal motion. There are few, if any, examples of elaborate mating behaviour at these depths. No dances. No displays, just presence, proximity, timing. Stillness in Challenger Deep is not only about energy, it's also about safety. Motion attracts. Even in darkness, predators can detect vibrations. Chemical trails disperse faster when the body moves. For a small, soft-bodied organism, being still can mean being invisible. There is something counterintuitive about this for humans. We often associate life with activity. We measure health by heart rate, movement, alertness. But in the trench, life is measured differently. It's measured by persistence, continuity, the ability to remain. And not moving is how that persistence is achieved. The animals here are not less alive. They are differently alive. They exist at a level of function where each action must be weighed against cost. They have mastered a mode of being that doesn't rely on constant change, that doesn't equate survival with struggle, that has learned, over millions of years, that staying in one place is often the smartest move. To the observer, this may feel alien, but to the trench, it's normal. Stillness is not absence, it's presence without disturbance. It's a way of inhabiting space without altering it, of waiting, not because there is no choice, but because waiting works. And in the trench, waiting is what most of life does. It begins with a descent, a body, once warm and filled with motion, now still. Far above the trench, in open water that still receives sunlight, a whale dies. It might have lived for decades. It may have carried the scars of migration, the rhythms of feeding and calling, the memories written into flesh and fat. But all of that ends in silence. And then the fall begins. When a whale dies at the surface or in mid-water, its body loses buoyancy slowly. Gases form as decomposition starts. The animal may float for hours, even days, but eventually those gases escape or are consumed. The balance tips, and a carcass weighing tens of tons begins to sink through the ocean. This process isn't fast. It can take hours for the body to reach the deep sea. Along the way, scavengers gather, Sharks bite. Fish circle. Flesh is torn free. Each layer of ocean it passes through leaves its mark, but not every carcass is consumed before it hits bottom. In some cases, most of the body survives the descent, a massive package of organic material carried downward by gravity alone. When it reaches the Hadal zone, the impact is quiet. There is no splash, no plume of silt rising in slow motion, just a slow settling into soft sediment, a slight shift in angle, and then stillness. The trench receives it without reaction. The water pressure is unchanged. The darkness remains total. No alarms are triggered. No system rushes to respond. But the arrival of a whalefall is one of the most significant events the trench will experience for years, possibly decades. It is not just a body. It is a temporary ecosystem, a feast in a land without food. The first to arrive are the opportunists, amphipods, deep-sea isopods, and scavenging fish detect the chemical signature released by the decomposing flesh. Even in darkness, these signals travel. Molecules drift through the water. Bacteria bloom on the surface of the skin. In response, the scavengers gather. Not in swarms, but in careful measured proximity. Some dig directly into the flesh. Others enter through the mouth or wounds opened during descent. They consume the soft tissue, the blubber, the muscle, the organs. This stage may last weeks, depending on temperature, depth, and the number of consumers. At Hadal depths, where metabolism is slow and feeding is deliberate, it may take longer. But the flesh is rich in fat and protein. Every gram provides energy far beyond what the local sediment can offer. As the carcass is reduced, a second community begins to form. These are the enrichment opportunists, organisms that thrive not on the meat, but on the organic soup that seeps into the surrounding sediment. The ground around the whale becomes chemically altered. Sulfides increase, ammonia levels rise, bacteria colonize not just the bones and skin, but the mud itself. Small worms, mollusks, and microbes move in. This secondary community may include species not found elsewhere in the trench. Some organisms may exist only around whalefalls, waiting years between events. Others may be generalists that shift roles depending on opportunity. Either way, the carcass has begun to reshape the seafloor. A once flat patch of mud becomes irregular, surrounded by tunnels, pits, bacterial mats, and the slow churn of feeding behaviour. The bones remain. These are not fragile. Whale bones are massive, dense and packed with lipids. They do not decay easily, but they are not inert. Inside those bones is a reservoir of energy, oil and collagen trapped in hard structure, and certain organisms have evolved to access it. Osedacs, also known as bone-eating worms, are among the most specialised. These worms have no mouths, no stomachs, and no eyes. Instead, they grow root-like structures that burrow into bone and form symbiotic relationships with bacteria capable of breaking down fat and protein. The worm provides shelter and access. The bacteria perform the digestion. Together they consume what most animals cannot reach. Over time, Osedacs and other similar species colonize the skeleton. They don't spread quickly. Growth is slow, but given time, they transform the structure. Bone softens, cavities appear. Eventually, the skeleton collapses in on itself, becoming a scaffold for microbial life. This stage can last decades. Even after all visible tissue is gone, the bones remain active, chemically, biologically, ecologically. They release compounds into the water. They provide shelter. They host bacteria that may not exist anywhere else in the ocean. For the trench, the whalefall is no longer a meal, it's infrastructure. And then there is the long tail of absence. After years, the nutrients run out. The bacteria slow their activity. The Osedacs die back. The scavengers stop visiting. The sediment begins to reclaim the space. In time, only fragments of bone remain, indistinguishable from other debris scattered across the seafloor. The trench closes around the memory of the whale. but during that time, the fall sustained life at a level otherwise impossible in this part of the ocean. The numbers tell the story. A single whale carcass can introduce hundreds of kilograms of carbon to the seafloor, more than the normal marine snow delivers to that same area in decades. In surface terms, it's as if a grocery store landed in the middle of a desert. But in the trench, where the organisms are adapted to need almost nothing, even a fraction of that bounty can reshape the local food web for years. Not every whale fall reaches the trench. Most decompose or are consumed at shallower depths. But when one does arrive, the effect is profound. It's not just about feeding mouths, it's about activating systems, waking up dormant bacteria, attracting rare species, creating gradients of chemistry that allow new processes to begin. For scientists, whale falls are more than curiosities. They are natural experiments. They reveal what's possible in a nutrient-limited environment. They show the range of specialization that has evolved around one of the rarest but richest events in the deep ocean. They also hint at the possibility of unknown species, organisms so specialized that they appear only when these falls occur. Capturing these events is difficult. Submersibles may return to a location multiple times before detecting a fall. Some are discovered by accident. Others are inferred from chemical signatures. But each time a new one is found, it expands the map of how life functions at extreme depth. The role of whale falls also raises questions about connectivity. If trench life depends partly on surface death, what happens when those surface systems change? As whale populations fluctuate due to human activity, climate change and shifting ecosystems, the frequency of whale falls may also shift. What seems like an isolated Hadal ecosystem is in truth connected to processes happening thousands of meters above, even on the other side of the planet. And that raises another point. Life in the trench is not isolated by depth alone. It's linked through time. A whale that dies today may support a community that still exists a decade from now. A trench-dwelling amphipod may encounter a food source only once in its lifetime. A bone-eating worm may spend a year growing into a vertebra that drifted from the open ocean in silence. Nothing here is fast. Nothing is wasted. Every molecule of carbon from that fallen whale will pass through dozens of organisms before it leaves the ecosystem, if it ever does. And many of those organisms may depend on that molecule to reach maturity, to reproduce, to persist. The whale, in death, becomes a system. Not an anomaly, but a cycle. A rare reminder that even in the deepest, quietest places on Earth, large events still ripple outward. That the fall of a single animal can awaken an entire stretch of the trench, and when it's over, when the skeleton is gone, the mud is smooth again, and the only evidence is the genetic memory of those who fed there. The trench returns to its quieter state, but something has changed. A generation of life has passed through. A sequence of interactions has unfolded. A system has been fed, and it will wait again, in stillness, for the next body to fall. On the surface of the earth, soil is alive. Beneath our feet, countless microbes break down organic matter, cycle nutrients, and form the invisible infrastructure that supports plant and animal life. We rarely think about it, but dirt breathes, it digests, it changes with time, it tells stories. In the deepest part of the ocean, where light never reaches and movement slows to near stillness, the equivalent of that living soil exists as mud. Cold, heavy, layered sediment stretching across the trench floor in an unbroken expanse of grey. To most observers, it appears featureless, flat, uniform. But that surface hides one of the least understood and most biologically active systems on the planet. In Challenger Deep, the mud isn't just a resting place for fallen particles. It's a layered archive of chemical and biological history. A slow build-up of marine snow, mineral dust, microscopic remains, and traces of distant surface events. Each layer settles, compresses, and transforms under the crushing weight of the water above, But buried within those layers are microbes, trillions of them, living, multiplying, altering the chemistry of their environment, even in conditions that would be lethal anywhere else. These microorganisms aren't loud, they don't leave visible trails, their activity isn't captured in dramatic video feeds. But if life on Earth has an outer boundary, a final limit before the line is crossed into total sterility, this mud may be where that line wavers, and possibly stretches further than anyone expected. Microbes in trench sediments fall into several categories. Some are generalist decomposers, feeding on organic particles as they slowly decay. Others specialise in breaking down specific compounds, including sulfides, methane, and ammonia. A smaller number are autotrophs, organisms that can produce their own food using chemical energy, independent of sunlight. It's the presence of these autotrophs that first raised questions among researchers. Without photosynthesis, there shouldn't be enough energy entering the system to support continuous microbial growth. The available organic material is minimal, surface inputs are scarce and patchy, and yet these microbes persist, not just in the upper few centimetres, but in layers measured in metres, even dozens of metres below the sea floor. Samples pulled from the trench floor often show living cells more than 10 metres down. Some of those cells are active, others may be dormant. But either way, they're present in concentrations that surprise researchers. This depth corresponds to thousands of years of sediment accumulation. It means some microbes have been isolated from the surface for centuries, possibly longer. To access these layers, scientists use gravity corers, long, narrow tubes designed to penetrate the mud and return samples in vertical slices. The goal is to preserve the layers without disturbing their sequence. Each centimetre pulled from the core represents years, decades, sometimes centuries of deposition, and each contains its own microbial fingerprint. The microbes aren't evenly distributed. Surface layers are more active, more populated, more diverse. As you go deeper, oxygen levels drop, organic material becomes more degraded. Competition increases, but life continues, slowly, quietly, and sometimes using chemical pathways still not fully understood. In some cases, researchers find microbes that metabolize compounds previously thought unusable, breaking down long-chain hydrocarbons, metals, or complex polymers. Others appear to fix nitrogen or use sulfur compounds as electron donors in the absence of oxygen. These chemical strategies suggest that the trench sediment isn't just a passive storage space for nutrients, it's a functioning biogeochemical reactor. One of the biggest surprises is the persistence of metabolism at great depth. Even in layers more than 100,000 years old, microbial activity is sometimes detectable. These are not fast processes. Some cells may divide only once every 100 years. Others might remain dormant for even longer. But the fact that any activity remains at all, that enzymes still function, that DNA can still replicate, that cell membranes remain intact, challenges long-held assumptions about the limits of life. This zone is often referred to as the deep biosphere, a realm of life beneath the obvious, sustained not by energy from the sun, but by the slow burn of chemistry, by the reworking of molecular leftovers, by reactions occurring one atom at a time. And Challenger Deep may host one of the most extreme examples of it anywhere on the planet. To fully understand what's happening down there, scientists look at more than just cells. They examine isotopic signatures, analyse metabolic byproducts, and measure the ratios of gases like methane and hydrogen. They track the movement of trace elements. They run incubation experiments in pressurised chambers, mimicking trench conditions in laboratories above. These methods are slow. The data is dense, but patterns are emerging. One pattern is that many trench microbes carry genes associated with stress resistance, proteins that protect against pressure, cold, and chemical damage. Another is the presence of horizontal gene transfer, the sharing of genetic material between unrelated organisms, at rates higher than expected. This suggests a system where adaptation is constant, where microbes respond to new inputs, organic fragments, mineral deposits, shifts in chemistry, not with movement, but with molecular change. And what they're responding to isn't just food. The trench floor is geologically active. Slow, deep-seated processes continue to reshape the area. Mud volcanoes, small faults, and plate subduction events may create localized changes in temperature, gas concentration, and mineral availability. Microbes are sensitive to these changes. They respond with blooms, shifts in dominance, or metabolic reprogramming. The mud, in this sense, is not uniform. It's a patchwork of microenvironments, each offering a slightly different version of the deep-sea challenge. One mystery still being studied is whether some of these microbes participate in previously unknown chemical cycles, for example, transforming deep inorganic compounds into usable nutrients in ways that bypass known steps. These cycles, if confirmed, could help explain how life persists at such low energy input. They might even reveal new principles of biochemistry that apply beyond Earth. This leads to another layer of interest: astrobiology. Because if life exists in the sediments of Challenger Deep, where pressure exceeds 1,000 atmospheres, where light has never reached, where organic input is rare and sporadic, then similar life might exist in the subsurface oceans of other planets or moons. Europa, Enceladus, and even the ancient seas of Mars have been proposed as potential analogues. Studying mud microbes in Earth's deepest trench becomes a way of asking whether biology is universal. Not in shape or species, but in strategy. The organisms themselves, meanwhile, remain mostly nameless. Their genomes may be sequenced, their behaviour observed, but they are rarely visible under standard microscopes. They do not glow or swim. They do not grow in petri dishes. Many exist only in environmental DNA traces, sequences extracted from soil and matched to no known organism. They are effectively invisible, and yet their impact is tangible. They influence the chemistry of the trench. They recycle nutrients. They make other forms of life possible by preparing the sediment, breaking down compounds that would otherwise be toxic, releasing small molecules that larger organisms can absorb. They soften what the ocean sends down. They make the difference between a place that just holds matter and a place that hosts life. Without them, the trench would be inert, a graveyard. Instead, it's an ecosystem, not a vibrant one, not fast or obvious, but living, slow, strange, and steady. When submersibles sample the mud, what they retrieve is not just clay and silt. It's a scroll of life's persistence. Each millimetre of depth adds another line to the story. A pulse, a cycle, a buried decision made by something too small to see, too slow to measure, too vital to ignore. And the deeper the sample goes, the more profound the questions become. At what depth does life stop? At what age does metabolism fail? Is there a boundary, a final layer of sterile rock where even the hardiest microbe can no longer function? So far, no one has found that line. As long as sampling continues, activity remains, and perhaps that's the most mysterious part. Not that microbes exist in this place, but that they do so with no audience, no sunlight, and no assistance. They are in every sense alone, operating on rules they helped write, under pressures no surface organism could tolerate, in conditions that stretch the concept of habitability to its edge. But they endure, and as long as they do, the trench remains more than a geological depression. It becomes something else, not a void, but a volume, a living body, one filled with questions not written in movement or shape, but in layers of mud that breathe, digest, and remember. No human has ever seen Challenger Deep with their own eyes. Not directly, not without help. The pressure at the bottom is too great, the darkness too absolute, the distance too far. And so, when we want to observe this place, we send machines. They go where our bodies cannot. They carry our sensors, our cameras, our curiosity. and they become our eyes in the abyss. The first steps were cautious. For most of history, the trench was known only as a theoretical low point, a place measured by sonar but not truly observed. It wasn't until 1960 that the first humans visited Challenger Deep, Don Walsh and Jacques Piccard aboard the Trieste. But even that historic dive relied heavily on machine systems. The pressure was too high for anything else. The Trieste was a bathyscaphe, a free-diving vessel with a steel pressure sphere suspended beneath a large gasoline-filled float. The float provided buoyancy without compressibility. The crew cabin was barely large enough for 2 people, with thick metal walls to withstand over 1,000 atmospheres of pressure. At the bottom, they stayed for just 20 minutes. The visibility was poor. The observations were brief, but it proved the point. We could reach the trench. For decades afterward, no one returned. The risks were too high, the costs too steep, but machines continued the work. Early unmanned probes were simple, pressure-resistant housings filled with sensors and timers. They recorded temperature, salinity, depth, and returned with data that hinted at what might exist far below. But they couldn't see, they couldn't move. They were tools, not explorers. That changed with the development of remotely operated vehicles, or ROVs. These machines could be tethered to ships above, controlled in real time through fibre optic cables. With cameras, lights, manipulators and sampling tools, they became our first true operators in the deep. But even these had limits. Most ROVs weren't designed for Hadal depths. Pressure housings failed, buoyancy systems collapsed, cables snapped under tension. The deeper the trench, the more specialised the machine had to be. So engineers adapted. New syntactic foams were developed, materials made from hollow glass microspheres embedded in resin. These provided buoyancy that could survive extreme pressure. Cameras were redesigned with thicker housings. Electrical systems were sealed, often in oil, to prevent crushing. Even simple bolts and connectors had to be reimagined. One of the key developments was the autonomous lander. These are free-falling platforms equipped with instruments and weights. They sink to the bottom, conduct their mission, then drop ballast and return to the surface. There's no tether, no human guidance, just a timed sequence of operations. Collect a sample, take a photo, measure a gradient, surface. Landers revolutionized trench science. They could be deployed in multiples. They were relatively inexpensive compared to piloted submersibles, and they could sit on the seafloor for hours or days, observing without interference. Some carried bait to attract animals, others took core samples of sediment. A few deployed hydrophones, capturing the faint low-frequency sounds of the deep. Then came full-scale Hadal ROVs. These machines were built from scratch for the trench, not adapted, but designed with the abyss in mind. One of the most advanced was Kaiko, developed by Japan's JAMSTEC agency in the 1990s. It was among the first to reach Challenger Deep repeatedly. It carried cameras, robotic arms, and a suite of environmental sensors. It collected biological and geological samples never seen before. But in 2003, Kaiko was lost. A failure in its tether led it to sink uncontrollably. It was never recovered. Other vehicles followed. Nereus, built by Woods Hole Oceanographic Institution, used a hybrid system, operating as both an ROV and an autonomous vehicle. It reached Challenger Deep in 2009, gathering images and data that added new layers to our understanding. But in 2014, it too was lost, crushed by pressure during a deep dive. These failures weren't setbacks, they were lessons. Each loss taught engineers more about the environment they were working in. The trench isn't just a deep place, it's an extreme system. The water pressure is over 100 times what we experience at sea level. Any air-filled space is crushed. Electronics are tested to their limits. Even titanium can deform under the wrong conditions. Every machine that operates here must be overbuilt. Every joint, every seal, every cable must account for forces that most environments never exert. And beyond the pressure, there's the challenge of communication. Radio waves don't travel well in water. Real-time data transfer is limited. Every mission is a negotiation between what's possible and what can survive. And still, the machines keep coming. In 2012, James Cameron descended solo to Challenger Deep aboard the Deep-Sea Challenger. Though piloted, the vessel was still essentially a machine. It used vertical orientation to reduce stress, carried on board batteries and lights, and featured custom cameras to capture the descent. His dive gathered samples, images and video. But it also demonstrated the role of private innovation in Hadal exploration. Since then, new technologies have accelerated. Modular landers can now be assembled and adapted on site. 3D printing allows for custom pressure housings. AI-guided autonomous vehicles are being developed to map the trench floor in detail, not just to visit it, but to understand its shape, its contours, its living patterns. And with every mission, more is learned. We now know that the trench floor isn't featureless. It includes ridges, pits, and even small landslides. Some machines have captured footage of microbial mats, faint coatings on rocks or sediment that glow under certain lights. Others have recorded scavengers gathering around bait, confirming behavioural patterns never seen before at this depth. Sampling tools have improved. Robotic arms can extract rock fragments or deploy chemical sensors. Some vehicles carry traps for amphipods. Others collect water at different depths, preserving the chemical gradient from surface to trench. There are even experiments to test how plastics degrade at Hadal pressures, showing not only what the trench is, but how it responds to human input. The machines themselves are now part of the system, not in a biological sense, but in a presence that reshapes what we know. Without them, Challenger Deep would remain a point on a map. With them, it becomes a space of questions, measurable, observable, complex. Yet despite all this progress, most of the trench remains unexplored. Its total area spans hundreds of square kilometres. A single lander footprint covers only a few square metres. It's like trying to understand a forest by looking through a keyhole. Machines give us access, but the view is still narrow. The future may change that. Swarm robotics, fleets of small autonomous machines, are being tested. These could map large sections of the trench at once, communicating with each other, adjusting in real time and responding to terrain. Pressure-tolerant sensors are becoming smaller, cheaper, more robust. Even battery technology is improving, allowing for longer deployments and deeper dives. Some projects aim to leave sensors in place for months or years, building a kind of observatory at the bottom of the world. Others are focused on return samples, hoping to bring back intact biological material for study without decompression damage. And some are just listening, capturing the low, distant sounds of tectonic movement, sediment shifts, and the occasional unknown event. These are not just engineering challenges, they're philosophical ones. What does it mean to observe a place we cannot enter? How do we design tools that act as proxies for our senses, our intentions, our scientific instincts? Because every machine in the trench is more than a device. It's a translator. It converts pressure into data, darkness into image, isolation into understanding. And in doing so, it reminds us that exploration doesn't always mean presence. Sometimes it means construction, of tools, of systems, of new ways of seeing. The machines are not passengers. They are the explorers. They drift, they land, they sample, they return, and because of them, we know that the trench is not empty, that it hosts life, that it changes, that it records time in sediment, in chemistry, in pulses of energy barely detectable. We know this because a machine once touched the bottom and came back with a piece of the story, and next time another will follow. The trench is deep, beyond imagining for most. A place further below sea level than most commercial aircraft fly above it, nearly 11 kilometres down. The pressure is crushing, the light is gone, and the temperature is barely above freezing. And yet, even here, far from the coastlines, ports and flight paths of civilization, the surface still speaks. It speaks not in words, but in fragments, traces, signals that drift and settle, pieces of a world far removed but never truly disconnected. Because in an enclosed system like Earth, separation is a matter of time, not distance. Sooner or later, what happens above makes its way below. One of the most visible of these surface echoes is plastic. When researchers first began retrieving sediment samples from Challenger Deep, they expected silt, clay, and organic fragments. What they found, alongside those natural layers, was polymer, tiny filaments, microbeads, fragments of plastic film. Not just a few, but measurable quantities, suspended in mud that had not seen daylight in centuries, embedded in the feeding paths of amphipods, caught in the folds of scavenged bait. The plastic came not from direct dumping, but from the gradual degradation of waste discarded at or near the ocean surface. Over time, sunlight and wave action break down larger pieces into smaller ones. These microplastics become neutrally buoyant, drifting with currents. Some are consumed by marine life and passed along food chains. Others aggregate with organic material and sink. Eventually they reach the bottom, and there they stay. Plastic doesn't degrade easily under these conditions. The cold slows chemical reactions. The pressure compacts rather than breaks down. Microbial communities that might consume organic polymers don't digest polyethylene or polystyrene, so the plastic remains, inert but present, and not just in small quantities. Some amphipods captured from trench depths contain microplastic particles in their guts, some contain dozens. There's no way to expel them. The digestive systems of these animals are slow and simple. Once ingested, the material stays. Whether it causes harm is still unclear, but it changes the internal chemistry. It displaces usable nutrients. It lingers. Chemical traces from the surface also arrive in less visible forms. Mercury, for example, enters the atmosphere through industrial activity. It falls with rain, accumulates in surface water, and binds to organic matter. That matter becomes marine snow, drifting slowly downward. In Hadal sediments, mercury concentrations have been found at levels comparable to surface waters, a signal of how far contamination can travel in a closed system. Other persistent organic pollutants follow a similar path. Dioxins, flame retardants, PCBs, compounds that resist breakdown in the environment, have been detected in trench organisms. These chemicals were manufactured for durability, for safety, for resistance. And now they've arrived in a place no person walks, no factory vents, no runoff pores. There are also biological echoes. Some microbial DNA retrieved from Hadal samples shows close similarity to species found in upper ocean layers. Whether these microbes survived the descent or simply left traces in the particles that sank is still under study. But the genetic signal is clear. The deep biosphere contains threads from the surface web. In some cases, these visitors may adapt. Trench conditions select harshly, but they do not erase potential. A microbe that attaches to a piece of descending detritus might find itself, by chance, in a viable microenvironment, trapped in a pocket of organic material, shielded by a fragment of shell or bone. If it can metabolize, it may reproduce. If not, it becomes part of the sedimentary record. Sound travels too. Though the trench is among the quietest places on Earth, it is not absolutely silent. Hydrophones left at depth have picked up low-frequency rumbles, not from within the trench, but from the surface. Ship engines, sonar pings, even seismic air guns used for oil exploration. These sounds lose energy as they descend, distorted by temperature gradients and water density. But they arrive, faint and filtered nonetheless. In rare conditions, surface noise can propagate across long distances using a phenomenon called the SOFAR channel, a natural acoustic waveguide in the ocean that bends sound waves and extends their travel. Even explosions, natural or man-made, can register at depth. Volcanic eruptions, underwater mining, testing ranges. The trench doesn't echo loudly, but it hears. What impact these sounds have on Hadal organisms is difficult to assess. Most lack traditional hearing, but many respond to vibration. The sensitivity of deep-sea species to pressure waves and mechanical disturbance is not well understood, and because their environment is normally so quiet, even a low-level pulse may register as significant. Another form of echo is nutrient fluctuation. Events at the surface, like seasonal phytoplankton blooms or large mortality events, influence the volume and composition of marine snow. A bloom means more organic particles. A die-off means more falling biomass. These events ripple downward over time. After a large surface event, sediment cores sometimes show a corresponding spike in certain isotopes or compounds. A pulse of nitrogen, a brief increase in lipid residues, a trace of chlorophyll breakdown. These signatures can be dated, creating a kind of history book embedded in mud. Each layer a faint echo of a surface condition no Hadal organism ever saw. Even the most intimate chemical cycles in the trench carry surface fingerprints. Carbon in trench organisms can be traced isotopically to surface sources. Its ratios reflect photosynthetic origins, the pathways of marine snow, the selective feeding of midwater organisms. What seems distant is actually inherited. The energy that powers trench life began as sunlight, captured at the surface, repackaged by life, and delivered, particle by particle, over time, and there are artificial materials. In 2019, researchers found a plastic bag on the floor of the trench, fully intact, partially buried in sediment but recognisable. It did not drift down recently. It had been there for years. It had passed through every depth zone, survived every pressure increase, and landed without breaking. Its presence was symbolic, a reminder that human presence is not limited to where we stand. Other items, fishing lines, packaging fragments, synthetic fibres, have also been recorded. Not many, but enough to show that even in a place with no traffic, no settlements, no activity, debris still arrives. In this way, Challenger Deep is not a closed system, it's a receiving one, a sink, a point where gravity, time and human behaviour intersect. Not in a dramatic way, but in accumulation, in drift, in arrival. What this means for life in the trench is complex. On one hand, the inputs can provide energy. A fallen fragment of organic waste might support microbial growth. A sunken carcass becomes an ecosystem. But human material, synthetic, persistent, inert, doesn't follow the same rules. It displaces. It adds compounds that were never part of evolutionary history. And while the effects may be subtle, they accumulate. In studying these echoes, scientists face a paradox. Every mission to the trench brings new knowledge, but it also brings risk. A submersible may leak oil. A sampling arm may disturb sediment. A lander may lose a component. Each effort to observe becomes, in some small way, an act of participation. This has led to increasing care in how deep-sea research is conducted. Tools are sterilised. Materials are tested for contamination. Chemical traces are used to distinguish human input from environmental signal. The goal is to measure without altering, to understand without disturbing. But the echoes remain, not just from human activity, but from the Earth itself. Tectonic shifts, sea level changes, large storms, all of these leave traces. The trench is a recorder, its mud is a medium, its water column is a filter, and so every time we sample it, we read backwards. We read the story of the surface, told in pieces, filtered through biology, chemistry and pressure. In this way, Challenger Deep reminds us that separation is an illusion, that no place is truly untouched, that even in darkness the world above continues to leave its mark, not with violence, not with presence, but with fragments. In 2018, a submersible returned from a dive into Challenger Deep with hours of video footage and sediment samples from the Hadal floor. Among the data reviewed by researchers and engineers was an unremarkable visual fragment. A wide shot of the seafloor, grey and quiet, dotted with small ripples and the occasional amphipod drifting past. But tucked into the corner of the frame, barely shifting, was something strange. Pale, rectangular, and slightly translucent. A plastic bag. It wasn't torn. It wasn't tangled or balled up. It lay there as if carefully placed, partially settled in the sediment, the top edge folded over itself. There were no markings visible. No label, no colour, no indication of where or when it had entered the ocean. But its shape was unmistakable. Something made by people. Something designed to be used once, perhaps for minutes, and then discarded. And now, here it was, 10,900 metres below sea level, resting at the bottom of the world. This wasn't the first time plastic had been recorded in the trench, nor would it be the last. But the image became iconic, not for its scientific value. There was no new measurement, no breakthrough analysis, but because it said something without needing to explain. Something clear, something quiet, something uncomfortable. To understand how that bag arrived here, you have to trace its journey from the surface. It likely began in a factory shaped by machines stacked in bundles shipped to a distribution centre, then handed out in a store, a market, a restaurant, and eventually thrown away. Whether that moment happened in Tokyo or Los Angeles or Manila, no one can say. But what came next is predictable. Wind moves light materials, rain flushes them into gutters, rivers carry them downstream, and from there, the ocean. Once in salt water, a plastic bag floats briefly. Sunlight, wave action, and microorganisms begin to degrade it, not by breaking it down completely, but by fracturing it, weakening its structure, making it fragile. But fragility is not disappearance. Weakened or not, the bag remains intact long enough to catch a current, to sink slowly under the right conditions, or to become entangled with denser organic material and pulled downward. As it sinks, it passes through layers of life, epipelagic, mesopelagic, bathypelagic, each zone marked not by hard boundaries, but by shifts in light, temperature, pressure, and biological density. At each layer, the bag may encounter drifting organisms, but it is not food. Its chemical structure resists digestion. Its shape provides little nutritional value, and so it continues downward. The transition from abyssal to hadal is steep. The trench walls fall like an open wound in the ocean floor, down through currents that twist without warning, through waters colder than ice, denser than any surface lake, until the bottom is reached. And then the bag rests. It doesn't move much, there's little current at the bottom. The sediment is soft but compacted. The bag doesn't bury itself, it doesn't degrade quickly, it simply sits, becoming part of the landscape, as if it had always been there. Nearby, amphipods scavenge. Microbes live in the sediment. Worms filter particles, and above, the ocean stretches upward in every direction. There is no sound. The discovery of the bag raised questions, some technical, some ethical. Researchers examined the footage and debated whether it posed a biological hazard. Could bacteria colonize its surface in unusual ways? Would chemicals leach from the plastic into the sediment? Would organisms mistake its texture for organic matter? The answers were partial. Microbes can indeed grow on plastic surfaces. These microenvironments are sometimes referred to as the plastisphere, colonies of bacteria that behave differently on synthetic substrates. Some are harmless, others are less well understood. In shallower waters, certain microbial communities on plastic have been linked to increased toxin persistence. Whether the same applies in the trench is unknown. Chemical leaching is also possible. Many plastics are made with additives, plasticizers, flame retardants, stabilizers that can slowly release into surrounding environments. These compounds don't behave predictably under pressure. Their behaviour at 100 atmospheres is still being studied, but their presence introduces new variables into an already complex chemical system. And then there's the question of physical interference. What happens when a scavenger brushes against the bag? When a burrowing worm encounters a corner of polyethylene in place of soft mud? The trench isn't empty. It's sparsely populated, but every square metre counts. Even a small object can become a disruption. Beyond the biology, the image triggered broader reflection. If a single bag can travel here, silently, invisibly, without guidance, what else has arrived? And if it hasn't arrived yet, how long will it take? Every year, millions of tons of plastic enter the ocean. Most doesn't sink to the Hadal zone, but some does. And as inputs continue, the probability increases. There is no cleanup plan. There is no agency tasked with retrieving debris from the trench floor. It would be impractical, expensive, and possibly more disruptive than leaving the material in place. So the plastic remains. Its presence becomes a marker, not of pollution as a surface issue, but of its total reach. The bag is not the beginning of contamination. It's the confirmation that contamination has no limits. And there's another layer, a symbolic one. The trench has always stood as an idea, a place of distance, extremity, purity, the farthest from the human hand. But the presence of plastic rewrites that idea. It suggests that there is no longer such a place, that every part of Earth is now part of the human sphere, not by habitation, but by influence. This doesn't mean the trench is ruined. The biological systems continue. Organisms adapt. Microbes metabolize. But the presence of the bag introduces a psychological change. The sense that even the deepest, darkest places are no longer separate. And yet, this realization also creates a strange kind of connection. When you look at the image, a single translucent bag in a grey field of mud, it feels familiar. Not in the way that fish or microbial mats do, but in the way that a sidewalk does. It is mundane, unremarkable, something any person could recognise, and that recognition bridges distance. The trench is no longer abstract. It's part of the same system that includes supermarkets, factories and landfills, not in design, but in outcome. The plastic bag at the bottom of the world tells us something about permanence, not just geological permanence, the kind that forms trenches over millions of years, but manufactured permanence, a material that outlasts use, that travels beyond its intent, that becomes inert but not absent. It also tells us something about untraceable origins. This object was not dropped by a ship. It was not delivered on purpose. It arrived as a result of normal processes, and that makes it more revealing. It wasn't an accident. It was a consequence. There's no single story to assign to it, no villain, no single location to blame. Its presence is the end result of millions of choices, none of them extraordinary, which means its meaning is collective. Scientists who study Hadal zones are now building models to track how materials move through the ocean to reach the trench. Not just plastics, but organic matter, metals, isotopes. The goal is to understand not just what arrives, but how long it takes, how long it stays, what happens after. Some speculate that in the far future, layers of trench sediment will record the Anthropocene in fragments. Flecks of plastic, traces of combustion byproducts, microscopic beads of industrial pigment. Long after the events themselves are forgotten, the trench will still hold the record. Layered, compressed, preserved. And the bag, now resting undisturbed, photographed once, possibly still there, is part of that record. It doesn't move. It doesn't decompose quickly. It may remain recognisable for centuries. It may become encased in sediment, its shape distorted but intact. It may break into smaller pieces, each one settling slightly deeper into the mud. But it won't vanish, and in this way, it has joined the trench. Not as an invader, not as a disaster, but as a reminder of how far things can travel, of how permanence behaves in a fluid world, and of how even the most remote places can end up holding what we leave behind. Challenger Deep is not a place where people can live. There is no shelter, no air, no food, and no light. The pressure is more than 1,000 times what the human body is built to withstand. The temperature hovers just above freezing, and the distance from the surface, both in space and complexity, makes it unreachable without extraordinary preparation. And yet, we go. Not often, not easily, not without risk, but we go. We build machines that can survive where we cannot. We fund missions that produce no immediate gain. We spend decades preparing a dive that may last only hours. We send cameras into darkness knowing there may be nothing to see. And we do it again and again. Why? The trench offers no mineral wealth that can be extracted with current technology. It holds no arable land, no usable energy, no real estate. It is not a place to conquer, settle, or transform. It offers little in return, at least nothing material. No economy turns on what happens there. No civilization has ever depended on it. There is no strategic advantage to occupying the bottom of the ocean. So again, the question, why go? There is no single answer, but part of it lies in what we've always done. Humans have a long history of moving into places that don't welcome us. Deserts, mountaintops, polar ice, low Earth orbit. Not because we need to escape the familiar, but because something in us compels us to know what's on the other side of distance. The trench represents a form of distance that isn't just physical. It's environmental, sensory, conceptual. It behaves differently. It challenges the assumptions we make about how life works, about what a place can be. Going there is not an attempt to survive. It's an attempt to understand. And understanding in science is often its own reward. Researchers who spend their careers studying the trench rarely describe it in emotional terms. They speak in data points, in chemical gradients, in pressure readings and microbial counts. But beneath the precision is a kind of reverence, not romanticized awe, but respect, for the complexity, for the scale, for the sheer difficulty of knowing anything about a place so resistant to measurement. There's something in that resistance that draws us. Challenger Deep does not reveal itself easily. Each visit brings only fragments, a sample, a clip of video, a few hours of data. There is no continuous stream of information, no live feed, no permanent station sending daily updates. Everything we know is built from effort, delay, and the limits of what machines can endure. And still, the knowledge grows. Because going to the trench isn't only about the trench. It's about testing what's possible. It's about developing materials that can withstand pressure for reasons that may apply elsewhere. In aerospace, in medicine, in planetary science. It's about understanding systems where energy is scarce. Processes are slow, and biology is stretched to its limits. These aren't just deep-sea questions. They're questions about resilience, about the architecture of life, about the thresholds beyond which complexity fails. And they're questions that can't be answered from the surface. Each expedition into Challenger Deep adds to a broader map, not of geography, but of conditions. It shows us what exists when sunlight is gone, when heat is minimal, when pressure crushes and isolation is complete. These are not conditions we were designed to inhabit, but they are conditions that exist elsewhere in the universe. The trench becomes a test case. For astrobiologists, it offers clues about what might survive on Europa, Enceladus, or in the subsurface oceans of distant exoplanets. For materials scientists, it demonstrates what failure looks like under real, continuous stress. For ecologists, it shows how systems adapt in the absence of most traditional inputs. But science isn't the whole story. There is a human dimension to exploration that persists even when utility is limited, a drive that predates modern instruments. It shows up in early maps, navigation records, in the stories of mountaineers, divers and astronauts. Not a hunger for novelty, exactly, but for contact, with something unmeasured, uninhabited, unclaimed. Challenger Deep has never been ours. We didn't discover it in the sense of finding something hidden. We identified it mathematically, confirmed it with sound, reached it with steel and foam, but it was always there. Its shape doesn't depend on our attention. Its chemistry doesn't change when we sample it. It does not acknowledge our presence, and still we go. Because being there, even remotely through machines, changes what we know about our own place in the system. It puts scale into perspective. It reminds us that Earth contains environments we don't control, that our world includes places that function without us, that life, in its many forms, does not need our permission to exist. There is something grounding in that. For all our technology, for all our reach, we remain surface creatures. Our biology is tuned to the atmospheric pressures and sunlight rhythms of a narrow vertical slice of Earth's environment. We can't survive underwater without assistance. We can't survive in deep space. We depend on built environments, suits, ships, systems, to reach beyond what our bodies can handle. And that's what makes places like Challenger Deep so revealing. They highlight the gap between what we are and what we imagine. They show us how much effort it takes to send even a camera to a place that microbes inhabit effortlessly. They teach humility, but also persistence, because we don't turn away from difficulty. We build toward it. We design better machines. We refine instruments. We accept failure as part of the method. And with every attempt, we reach a little further. There's also a philosophical aspect, one not always spoken, but present in the motivations of researchers, engineers and funders alike. If we don't go, how will we know what we missed? The trench could hold processes that alter our models of life. It could host microbes that carry enzymes capable of revolutionizing medicine. It could teach us how to engineer materials that function under pressure. Or it could simply confirm that life finds a way, even here. We go because we suspect the unknown is worth knowing, and because there are few things more human than that. Every time a lander sinks into the trench, every time a submersible descends beyond the light, it carries with it years of planning. It represents funding, research, coordination, design, and its return is never guaranteed. But when it comes back, when data arrives, when samples surface, when new species are described, the effect radiates, not just in journals or conferences, but in a quieter, broader way. It affirms that knowledge is something we can build from nothing, that patience, discipline and curiosity still have a place in how we define progress. The trench doesn't ask to be explored. It doesn't signal us. It doesn't need us. But we go anyway, not to take, not to alter, but to witness. Because knowing that life exists in such a place, slowly, differently, persistently, is a reminder that the world is bigger than our perception of it, and that there is value in the margins, in the extremes, in the quiet. We don't go to live, we go to learn, and sometimes that is enough. Beneath the floor of the ocean, past the reach of light and the noise of weather, there is a place where time moves without pause, but where its records remain almost untouched. Not because they are protected, but because they are ignored, buried, sealed by pressure, compressed by the weight of water and gravity. Challenger Deep, at the southern end of the Mariana Trench, is the lowest point in the Earth's crust, and one of the best preserved records of what has fallen through Earth's systems, not in relics or fossils, not in artifacts, but in sediment, chemistry, isotopes, and the microbial changes that trace every shift in what has passed above. The trench collects. That is what it does, and what it has always done. Not actively, not with purpose, but as a function of shape. Its slope and depth create a funnel, a long descent that gathers everything from dead plankton to microscopic minerals. Anything not buoyant enough to stay suspended, or small enough to avoid the draw of gravity, eventually settles, and once it lands, it rarely moves again. There are no sweeping currents in Challenger Deep, no tide strong enough to stir the seafloor. Movement happens slowly, by millimetres, sometimes not at all. The trench floor is a basin of stillness, and in that stillness, things accumulate. Each layer of sediment tells a piece of a story. Marine snow, falling particle by particle, compacts into thin bands. Some are rich in calcium carbonate, others are made mostly of silicious remains, the glass-like shells of diatoms. There are layers where organic matter dominates, and others where almost nothing remains but clay. These changes aren't random. They reflect what was happening at the surface when those particles formed. A spike in plankton productivity during a warm period, a sudden increase in mineral dust from a distant volcanic eruption, a shift in isotopic ratios during a global climate event. Each leaves its fingerprint, however faint, in the trench. To study this, researchers use core samplers, long cylindrical tubes that are driven vertically into the sediment. When retrieved, they contain columns of mud organised by depth, and by extension, by time. The deeper the layer, the older it is. Some cores pulled from the Mariana Trench contain sediment thousands of years old. Some may stretch much further back into periods not yet fully dated. Analysing these cores is a methodical process. Sections are sliced, freeze-dried, and analysed chemically. Carbon-14 dating reveals when the material was deposited. Stable isotopes like oxygen-18 show temperature fluctuations in the ocean at the time. Trace metals tell us about atmospheric composition. Even small changes in colour and texture can indicate shifts in erosion patterns on distant continents. It's not just Earth's natural processes that show up in the trench. Human activity leaves a clear layered record as well. In some cores, researchers have identified the so-called bomb spike, a sharp increase in radioactive isotopes caused by nuclear weapons testing in the mid-20th century. Carbon-14 and plutonium-239 from atmospheric detonations settled into the ocean, then slowly drifted downward. These layers now act as timestamps, unintentional signatures of a specific era. Other layers contain microplastics, fragments of synthetic polymers that were manufactured, used, discarded, and eventually pulled downward through the water column. Unlike natural particles, plastic resists degradation. It becomes part of the sediment record, not just chemically, but physically. A new kind of fossil, engineered and distributed globally. In one way or another, the trench now contains evidence of industrialization, fossil fuel combustion, synthetic chemistry, global agriculture, and mass-scale shipping. These markers are not just confined to the top few centimetres. They are being compacted, pressed downward with every year. They become part of the geologic archive. But the trench isn't only a passive record of surface activity. It also records what happens within its own ecosystem, and under its own floor. Challenger Deep sits on a tectonic boundary. The Pacific Plate is slowly sliding beneath the Mariana Plate, creating a subduction zone. As one plate descends, it drags surface materials with it. Not just rocks and minerals, but sometimes entire sections of seafloor sediment. Organic matter, microbial communities and mineral layers are folded downward, reheated and transformed. Some researchers believe that this process creates a kind of deep recycling, a way for biological material to enter the planet's interior and re-emerge later through volcanic activity. It's a long cycle, measured in millions of years. But it means that the trench isn't just a record of what's happened, it may be part of what happens next. Even now, trench sediments show evidence of chemical reactions that wouldn't occur at the surface. Under high pressure, water interacts with minerals differently. Microbes perform metabolism at energy thresholds far lower than those required at shallow depth. These reactions leave behind unique signatures, altered isotopic ratios, trace compound residues, shifts in pH. Together, they build a map of how matter changes at the threshold between biology and geology. The microbial DNA preserved in trench sediments also functions as a form of record. Not in the way that fossils do, but in the persistence of genetic material over time. Even if a microbe is dead, its DNA can remain for years. By sequencing DNA from different sediment layers, researchers can reconstruct how microbial communities have changed, how diversity shifts with nutrient pulses, how some species dominate during lean periods, how certain genes appear and vanish depending on chemistry. These data allow researchers to piece together past microbial ecosystems, not through bones or shells, but through strands of genetic code. That code reflects conditions at the time, pressure, temperature, chemical availability, and becomes another form of historical archive. And then there are the fossils. They are not common. Bones rarely make it to the trench intact, but traces remain. The hard shells of foraminifera, tiny single-celled plankton with calcium carbonate shells, are abundant in some layers. Their shapes change with ocean acidity, and their chemical composition reflects the conditions of the surface ocean where they lived. When found in Hadal sediments, they serve as time-stamped proxies for surface chemistry. Occasionally more recognisable remains discovered. Fish bones, the occasional tooth, even fragments of whale skulls, each a marker of a larger story. These pieces are rare, but when found they speak to the journey of organisms from the upper ocean to the deepest point, and what happens to matter as it crosses that vast vertical space. In its quiet way, the trench records mass mortality events. After algal blooms or jellyfish die-offs at the surface, particles rain down. If a whale dies and sinks, the trench may receive its bones. If a climate shift leads to changes in ocean productivity, that shows up in the organic content of sediment layers. Each of these inputs leaves a signal, not immediately obvious, not dramatic, but measurable. Over time, these layers add up. A centimetre of sediment in Challenger Deep might represent decades of accumulation, in some parts, even more. This means the floor of the trench is not only a physical low point, but a temporal archive, a compressed, layered record of what the Earth has passed through. And unlike many surface environments, the trench is relatively protected from disturbance. There are no floods to rearrange the layers, no scavengers large enough to churn the sediment, no plants to root and mix. Once something settles, it stays. And that makes the trench floor one of the most reliable long-term archives on the planet. Not all parts of the trench preserve the same record. Some areas accumulate sediment quickly. Others are shaped by small landslides or tectonic shifts that reset the layering. But the general pattern holds. What arrives becomes part of the archive. What becomes part of the archive tells us something about what happened, not just locally, but globally. Studying the trench as a time capsule is slow work. Samples take years to collect, process and interpret. But with each new layer, new storylines emerge, about climate, about ecosystems, about planetary cycles that move slower than human lifetimes, but more surely than any forecast. And now, more than ever, the trench's role as an archive has gained urgency. Because the pace of change above is accelerating, the sediment being laid down today contains not just plankton and silt, but industrial residues, synthetic fibres, and altered carbon signatures. Future researchers may find these layers and read them as we now read ice cores and tree rings. A record of change, framed by depth. Challenger Deep doesn't preserve memories. It preserves evidence. Physical, chemical, biological. No myth, no metaphor. Just the planet, writing its story one particle at a time. Every time a submersible returns from the trench, every time a lander surfaces with its small package of sediment, water or images, the analysis begins. Samples are labelled, tested, archived. Video is watched. Sensors are checked. The data goes into spreadsheets, maps, and reports. Eventually patterns emerge. Measurements are compared across years, across missions, across depths, and then the question returns. Could there be more? Because for all we've seen, what we've seen is limited. No matter how carefully planned, no expedition covers more than a sliver of the trench floor. No camera records more than a narrow field. No sediment core extends deep enough to capture the full history. Every machine, every instrument, Every human theory is constrained by materials, by energy, by pressure, by time. The trench is 11 kilometres deep and hundreds of kilometres long. It contains valleys within valleys, slopes within slopes, microenvironments shaped by angle, density, mineral content and history. There are parts no one has visited, areas no camera has scanned, layers of sediment no probe has sampled. Even where we've gone, conditions change over time. A microbe observed in one sample might not appear in the next. A layer of organic rich sediment might vanish a metre away. Pressure might not be the only force at play. Chemistry, tectonic stress, and seafloor topography all add variables we can't fully track. So we ask the question again, could there be more? Could there be organisms adapted to pressures slightly beyond what we've tested? Could there be ecosystems shaped around processes we don't yet understand? Metabolic cycles that use compounds not yet considered part of life? Could there be structures, communities, or interactions that are invisible to current instruments? Could there be deeper sections, steeper crevices, or temporary conditions that make some parts of the trench more extreme than others? And beyond that, could there be entire layers of life, tucked into rock pores, feeding on geochemical gradients rather than organic debris? We've already found microbial life meters beneath the seafloor, some of it active, some of it simply present. In some samples, cells exist where the energy availability is almost indistinguishable from zero, and yet those cells persist. That alone suggests we haven't found the lower boundary of biology, so it's reasonable to assume that more could exist, not necessarily in large forms, not in strange monsters or undiscovered fish the size of submarines, but in processes, in biochemistry, in genetic potential. We've sequenced DNA from trench microbes that shows no match to any known organism. Some sequences are close to known phyla, others drift further. In each case, the possibility remains open, that we've encountered biology that doesn't follow familiar taxonomies. Some of these sequences may belong to uncultured bacteria or archaea, groups that survive in very specific conditions and defy replication in lab environments. Others may be contamination, but the rest point to the existence of uncharacterized life. Not just individual species, but whole lineages. And what about viruses? Marine viruses are among the most abundant biological entities on the planet. In surface waters, their presence shapes microbial populations. In mid-ocean depths, they transfer genes, regulate community structure, and participate in nutrient cycling. But in the trench, little is known. Some viral particles have been detected in Hadal sediments. Their genomes suggest a range of hosts, from bacteria to archaea. Some carry genes that appear to help their hosts survive stress. Others seem to modulate metabolic function. But the diversity is likely underreported. We haven't developed the tools to search thoroughly. We don't know what we're missing. The same applies to chemistry. Many of the reactions occurring in trench sediments are inferred, not directly observed. We know the end products, we see the gas ratios, but the intermediates, the small steps in between, often escape detection. Could there be novel enzymes, unknown reaction pathways, metal-catalyzed processes that only occur under high pressure? These aren't speculative fantasies, they're informed gaps, areas where data is sparse, where instruments have limits, where assumptions still dominate models, and the trench does not exist in isolation. It connects to the broader ocean, to the tectonic processes beneath, to atmospheric and biological inputs above. Could there be interactions we haven't traced? Cycles that loop through time frames longer than human observation allows. Some isotopic studies suggest fluctuations that don't match surface records. Some microbial signatures hint at subsurface inputs. Methane seeps, though rarely observed, may play roles in shaping microbial communities. Iron and manganese nodules form over centuries, possibly seeded by microbial action. But what initiates these processes? What regulates them? Could biological activity be influencing mineral structures in ways we don't yet recognise? And then there's geology. Seismic activity along the trench boundary occasionally shifts the landscape. These events are rare but powerful. A fault line moves, a slope collapses, a buried layer is exposed. In these moments, chemistry and biology meet in new configurations. Has anyone recorded a trench quake in real time with full environmental instrumentation? Not yet. Could such an event produce sudden blooms of microbial activity? Could it release gases trapped for millennia? Could it trigger new biological or chemical conditions? Possibly, but without observation we cannot confirm, and without confirmation the door remains open. Could there be more? Even the basics, how many species live at the bottom, what they eat, how they reproduce, are not fully answered. We've identified amphipods, polychaetes, certain types of snailfish. But how many variations exist? How many niche feeders? How many symbiotic pairs? DNA sequencing reveals complexity, but visual records are scarce. Many organisms live hidden in sediment. Some are too small for cameras. Others avoid baited landers. What we've seen may be a sampling artifact, a portrait built from what's easiest to detect, not what's most abundant. Could there be organisms that fluoresce in spectra we can't detect? Could some trench microbes depend on long-term dormancy cycles, emerging only during rare nutrient pulses? Could entire ecological strategies exist that we haven't imagined? Every answer leads to new questions. Every confirmed measurement outlines the boundaries of what we know and what lies beyond. And still, we ask, could there be more? Because that question doesn't signal failure. It signals maturity, a willingness to admit uncertainty, a recognition that discovery is a process, not a result. Some researchers now propose permanent monitoring platforms in the trench, instrument arrays that could record over years, not hours. Others suggest return missions with higher resolution cameras, broader chemical sensors, more adaptable sample tools. Some want to explore further down into the sediment. Others want to go laterally, scanning broader swathes of the trench floor. There are proposals to map microbial genomes at scale, to study viral dynamics, to test new materials that can withstand the pressures long enough to record continuously. And all of these are driven by the same idea, that what we know is just a slice, that the unknown may still be deeper, quieter, or simply waiting. Not because it's hiding, but because we haven't looked hard enough yet. And so the work continues. Not in search of spectacle, but in search of process, of function, of truth buried in silt and pressure. Because the question, could there be more, is not rhetorical. It's methodological. It's the engine of inquiry. It's why landers are still being built, why cores are still being pulled, why data is still being studied long after the dive's end. The trench doesn't answer, but it responds with clues, with traces, with silence punctuated by presence. And every time we gather that presence, however faint, however fragmentary, we reframe the edge of what we know, not by finishing the map, but by confirming that there is still something to map. At the surface, the world is always moving. Clouds gather and disperse, winds rise and fall, currents churn, cities grow, devices blink, plans shift, data travels at the speed of light, schedules compress into hours, satellites orbit, airplanes crisscross, decisions are made and undone, and people, always people, are moving between tasks, between screens, between places. Noise is constant, mechanical, digital, social. Even silence at the surface is rarely complete. It's filled with hums, buzzes, background signals. Everything is in motion. Even the ocean from above reflects this restlessness. Waves fold and collapse. Surface temperatures change. Ships draw lines across the water. But far below, something else persists. Challenger Deep doesn't change quickly. It doesn't reflect the pace of surface life. It doesn't mirror our urgency. Instead, it offers something very different. A kind of stillness that resists interpretation. Not frozen, not lifeless, but calm in a way that feels increasingly rare. When a lander reaches the bottom, the first thing it records is how little seems to be happening. The water is not still in the absolute sense. There are minor flows, vertical mixing, diffusive currents. But compared to what we experience at the surface, it is nearly motionless. No wind, no sun, no tidal surge. The sediment sits undisturbed. Particles fall, but they do not stir up chaos. Movement, when it happens, is slow and direct. A fish passes, then disappears into the dark. An amphipod bumps against a rock, then continues. A microbial mat lines the top of a buried stone, and around it the quiet returns. This stillness is not absence. It's a different kind of presence, one that doesn't need to assert itself loudly to be real. It contains activity, but it holds that activity in a frame of calm. It demands patience, not just from cameras or instruments, but from the scientists watching. It requires us to slow down. Surface science can sometimes reward speed. Fast results, fast publication, fast application. But deep-sea work doesn't move like that. Instruments fail. Samples are delayed. Missions take years to plan. Data is sparse. And everything must be interpreted carefully because there are no second chances in places like this. You drop a probe, you wait, you collect what it gives you. You look, you think, and you ask, what is happening here, and how do I understand it? The answer is often slowly. This patience shapes the way we understand the trench. Every meaningful discovery, a new species, a chemical process, a tectonic signal, emerges not from a single moment, but from accumulated observation. It comes from paying attention over time, from noticing the detail that didn't match expectation, from comparing a sample today with a sample from 10 years ago. And the trench, for its part, continues its slow accumulation. It takes in everything. Particles from the surface, echoes of distant storms, material from landslides hundreds of kilometers away. It does not reject. It does not respond with disruption. It settles. It stores. And over time, it creates continuity. This continuity is not something we experience much in surface life. There, change is often the goal. Optimization, acceleration, novelty. But in Challenger Deep, change is so slow, it requires new tools just to detect. Chemical signatures shift by trace amounts. Biological communities evolve over millennia. Pressure stays constant. Darkness stays absolute. And in this contrast, there's something valuable. A reminder that not all systems move at the same speed, that not all knowledge arrives quickly, that not all environments respond to our presence. Some simply are. The trench doesn't offer feedback. It doesn't care if we observe it. It doesn't adapt for our understanding. It continues at its own pace, under its own conditions. And that constancy, strange as it may sound, becomes a source of insight, because it strips away noise. It removes variables. It gives us a chance to look at systems operating under extremes, without interruption, without fast feedback loops, without human shaping. And in that stripped-down version of the world, new relationships become visible. We see how life adapts to long-term scarcity. We see how geology moves matter slowly but relentlessly. We see how isolation doesn't mean absence, and how distance doesn't mean disconnection. We learn to think in longer timelines, to accept that some processes cannot be sped up, that some questions are best answered with observation, not intervention, that some systems resist our usual methods, and that in resisting, they teach us something, not about the trench only, but about ourselves, because for all its distance and depth, Challenger Deep is still part of the same Earth. The same planet that produces the storm above produces the silence below, the same gravity, the same ocean, the same biochemistry. It is not alien, but it is different, and that difference matters. It reminds us that complexity doesn't always look the way we expect, that motion isn't always visible, that significance isn't always fast, and in a world where much of science is built on action, on experiment, on disruption, on transformation, the trench teaches us how to watch, how to measure without altering, how to understand without changing what's being studied. This kind of science requires humility. It requires accepting that we may not see results in our lifetimes, that discoveries might come later from someone else, analysing data we collected without knowing its future value, that what matters isn't always what announces itself loudly, but what persists quietly. Even the act of reaching Challenger Deep reflects this. No one goes quickly. Submersibles descend over hours. Landers take longer, there is no shortcut, no express lane. You move slowly, you plan, you account for everything. Pressure, temperature, time, battery life, mechanical stress. And still things go wrong. But when they work, when the instruments reach the bottom, when the data comes back, it is always a version of the same thing. Stillness. Stillness filled with trace elements, soft gradients, rare life, slow processes, and the unmistakable sense that what you're looking at is not waiting for you. And yet, it has recorded everything. Storms on the surface come and go. Ships cross the Pacific in days. Aircraft trace arcs from continent to continent. Economies shift. Technology updates. News changes by the hour. But in Challenger Deep, the storm doesn't reach. Its echo might. The particles might. The pressure wave maybe. But the place itself continues unaltered, and in that it becomes a kind of constant. Not a retreat from complexity, but a deeper version of it. Not a blank void, but a full system operating outside our usual speed. This doesn't make it more important than surface life, but it does make it uniquely informative. Because when everything else is in motion, the existence of one system that moves slowly, quietly, consistently, offers a reference point. And science needs those, not just data points, but environments that show us what stability looks like under pressure, what life looks like when energy is scarce, what survival looks like without sunlight, without speed, without sound. So we keep studying, not because we expect a revelation, but because we know that even in stillness there is motion, even in quiet there is life, and even in a place without storms the memory of every surface event arrives, eventually, particle by particle, until it becomes part of the floor. The trench receives, the trench holds, the trench continues, and somewhere far above the storm moves on. If you're still with us, somewhere in the dark, somewhere beneath the surface of your own thoughts, thank you. Thank you for spending this quiet time with Science for Sleep. The trench will still be there tomorrow, and the day after that. Slow, silent, and full of things we haven't yet found. Just knowing it exists. Knowing that somewhere, far beneath the noise and speed of daily life, there is a place this calm can be enough. If you found this soothing, or simply stayed a little longer than you meant to, feel free to subscribe, like, or leave a comment. We make these not to chase algorithms, but to offer something steady in a world that moves fast. Until next time, sleep well, stay curious, and good night.